this is legacy approved. I had a vision before them folks had a clue. Thank God I still had ability when we didn't have a roof. I couldn't even think of stability, let alone had the tools to be making change, and it ain't that ancient a memory. Strange that I can't forget where I came, but don't know if they'll do the same and remember me till I'm painting a bigger picture, making some bigger figures. I can't get stuck in that lane that's deep, it'll be delivered. Trust me.
I've been working in mercy, Lord, trusting my process of monies, looking for progress and pushing forward. Know I might fall while I'm running. I pick myself up sometimes and pay that pressure no mind. Cause ain't no way I can work this hard, and I know my time is coming.
Look, feet all on the pavement, but these dreams feel so adjacent to this rut that I've been stuck in, begging Jesus, can you save him? And the mirror start to hate him, cause I really know he faking. What's the point of shots you taking when your purpose you evading? Unhealed scars, heart is made of gold, but I feel bronze. Should wash the dirt away for newest day, but it's still dawn. Talking to my peers to make it clear like who healed y'all. Was taking little baby steps at first, but I still crawl. Pain is deep inside, that's been something I feel more. I know I should be working, but these days I just chill more. Stuck in solitude in my residence, the truth is clear as evident. Boy, you know you haven't sinned, don't need no more evidence. You all outside your element, cause you got too arrogant. Your soul is in a deficit, boy, you know you delicate. Get back on your regiment, so pick yourself up. This was good for your development, and that's real.
I've been working in mercy, Lord, trusting my process of monies, looking for progress and pushing forward. Know I might fall while I'm running. I pick myself up sometimes and pay that pressure no mind. Cause ain't no way I can work this hard, and I know my time is coming. I've been working in mercy, Lord, trusting my process of monies, looking for progress and pushing forward. Know I might fall while I'm running. I pick myself up sometimes and pay that pressure no mind. Cause ain't no way I can work this hard, and I know my time is coming.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So welcome to this week. We're going to talk about number theory. Actually, before I forget, there are some handouts at the very back. So please raise your hand if you don't have any. Then one of us can actually come over and hand you out this sheet, which contains some facts about divisibility. Thanks a lot. And we will be using these throughout the lecture. So today we're going to talk about number theory. And this is a really different way of thinking, actually, but we will use the same concepts as you have learned before, like induction and invariance, stuff like that, to prove all the theorems. So what is number theory? Well, first of all, it's a very old science, one of the oldest mathematical disciplines, and only recently it actually got to have some more practical applications. So what is number theory? It's actually the study of the integers. And what are the integers? Well, these are the numbers 0, 1, 2, 3, and so on. So number theory got, there's some more over here. Another handout over there. So number theory got used actually in cryptography only about 40 years ago. And at the end of the second lecture, we will be talking about this application into cryptography. There are many applications in cryptography, but we will be talking about one of them to show you how useful this actually is. Now, cryptography is the study and practice of hiding numbers, and you can imagine how important that is. we have like medical data that we need to store outside in the cloud, right? So, gee, do we really want that? We actually want to hide our information. We do not want others who are not allowed to see my private information to see it. So this art of hiding information is extremely important, especially nowadays. And number theory actually will help us with it. So number theory is something, you'll be very surprised, that can be used to save, oops, I have to put this on, to save New York City in Dijk number 3, I believe. So let me start up again. So let's see where it plays. Maybe not.
Yeah, go ahead and grab it. Oh, you're the cop. Simon said you're supposed to be helping with this. I'm helping. But when are you going to start helping? After you get the bomb. Careful. Careful. Don't open it. What? I gotta open it. It's gonna be all right. Shit! I told you not to open it!
I trust you see the message. It has a proximity circuit, so please don't run.
Yeah, I got it. We're not gonna run. Now we turn this thing off.
On the fountain there should be 2 jugs. Do you see them? A 5-gallon and a 3-gallon. Fill one of the jugs with exactly 4 gallons of water and place it on the scale, and the timer will stop. You must be precise. 1 ounce or more or less will result in detonation. If you're still alive in 5 minutes, we'll speak.
Wait a sec! I don't get it. You get it?
No.
Get the jugs. Obviously, we can't fill the 3-gallon jug with 4 gallons of water, right?
Obviously.
All right, I know. There we go. We fill the 3-gallon jug exactly to the top, right? Okay, now, we pour that 3 gallons into the 5-gallon jug, giving us exactly 3 gallons in the 5-gallon jug, right?
Right. Then
Okay.
what?
Now, take the 3-gallon jug, fill that a third of the way up.
No, he said be precise.
Shit.
Exactly 4 gallons.
Copping 50 miles is running his ass off, and I'm out here playing kids' games in the park.
Hey! You want to focus on the problem at hand?
All right. You can imagine what we are going to do right here, right? So, you can imagine what's below this table. There's a bomb. You guys have to save 604 too. So we have the fountain here. Each tennis ball is 1 gallon of water. We have a big jug, 5 gallons and 3 gallons. So you all got to help me out here. So who has an idea of what we can do? So, well. All right, let's first do that. Fill up the 3-gallon. Let's pour it in the 5. Maybe someone else can continue over there.
If we do the same again, we'll end up with just 1 gallon in the 3-gallon.
Aha, so let's do that. Because that's true, right? We can only fill it up to 5 gallons, so only at most 2 gallons can add to this. Exactly 2 gallons, and 1 gallon is left. All right, next one. You like to? Take out the 5. Take out the 5, all right. And then what? Put the 1 over here.
Then fill the 3-gallon and put it into the 5.
All right. That's great. And then fill it up right here. Fantastic. So we actually have 4 gallons here. And luckily we are saved, right? So you saved, thank God, 604.2. So we can continue. So this is actually pretty amazing, though. How can we get 4 gallons out of a 3-gallon jug and a 5-gallon jug? And that's what we are going to talk about in more generality, actually. And if you would just change it a little bit, right, then things would get more difficult. For example, if you would change the 5-gallon jug into a 6-gallon jug, can we still get 4 gallons? No, why not? Everything has to be multiples of 3. That's exactly right. This is a multiple of 3, 1 times 3. This is 2 times 3. So if I do combinations with those, like pouring one into the other completely, or emptying or filling up, we always will have a multiple of 3 gallons in either one of those or both. So we can never have 4 gallons. So this is something that we would like to analyze a little bit more. And to do that, we're going to first of all start with the definition. Actually, you can put up the screen over here. So let me take that out. Can someone up there pull up the screen? Maybe not. Maybe later. All right, so let's go with the definition. We say and denote by M and a bar and A, we mean M divides A. And how do we define this? Well, we say that M divides A if and only if there exists an integer k such that A can be written as a multiple of M, namely k times M. So, if you look at this definition, we, for example, have that 3 divides 6, like what we just discussed. There's something interesting going on. Suppose A is equal to 0. Well, any integer will divide A, will divide 0. Why is that? Because I can take k to be equal to 0. So this is equal to 0 times any integer m. So m divides 0 for all integers. So that's kind of the exception, right? And we are going to use this to set up a theorem and analyze this whole situation over here. Now, in order to do that, we will need to sort of define what we can do with all this. So there are states. We will define a state machine. We will see what kind of possible transitions we can have. And once we have modeled all this very precisely, we can start proving stuff. Now, let me first of all write out what our assumptions are. So suppose we have a gallon jug. So in our case, A equals 3. And we have also a B gallon jug. And in our case, B equals 5, right? And we assume that A is at most B. That is sort of the situation that we are working with. And we would like to prove a theorem. Exactly what we noticed over here, that 3 divides both the 3-gallon jug and the 6-gallon jug. We would like to prove something like this. If M divides A, and also M divides B, well, then M should divide any result that I can get with the pouring and emptying and filling those jugs. So this is the theorem that we would like to prove, and we can only do that if we start to have a proper model for this. So let's go for that. And well, the state machine that we're going to use here looks like this. First of all, the states that we have are the number of gallons that are in these two jugs. So we will denote those by pairs. Pairs x, y. And X denotes the number of gallons in the A gallon jug. The number of gallons in, let me abbreviate that by the A jug. And Y is the number of gallons in the B jug. So these are the states, and the start state is exactly as it is right there. We have nothing in either of the jugs. So that's the pair 0, 0. So now we start to build up some mathematics here, right? So we express the state of this whole situation by a pair of numbers. Now we need to find out what we can do with it. So what are the transitions? The transitions are, as we have seen, right? We can just fill one of the jugs, we can empty those, and the other possibility is that we can pour one jug over into the other one as much as we can. So let's write all of those out. We can do emptying. Well, how does that change a state? If we have X gallons in this jug and Y gallons in that one, we can transition this into, for example, emptying the A gallon jug. So we will have 0. Or we can empty the B jug. Well, filling is something similar. But now we are actually pouring in more water from the fountain, essentially, right? All those tennis balls here. And we can fill up, say, the A gallon jug up to 8 gallons and leave the B jug as it is. Or we can fill up the B gallon jug and leave the A gallon jug as it is. So these are these two transitions. And the pouring of one jug into the other is actually a little bit more complex. So let's have a look. So how does pouring work? Well, suppose we start with X and Y. So let's have a look here. I don't know, suppose we have 2 balls in here and 2 balls in here. Well, in that case, I can say pour all of this over in here, right? So that's easy. But there's also another possibility, whether when I pour all of this over in here, but hey, I can only put in 1 ball because this is only a 3-gallon jug. So I'm left with only 1 gallon in this jug. So these are two situations that we need to explain. So let's first do the first example that I just did. I pour everything over into the other jug. So we have 0 gallons left in here and X plus Y gallons left in the other jug. And that can only happen if there is sufficient space, right? So this can only happen if X plus Y is at most B, which is the capacity of this B gallon jug. Now, if that's not the case, then I can pour in just a little bit, like just say 1 ball, like just 1 of these can go in here. So that's the other case. So XY will actually go to, well, let's just see how that works. How many gallons are left in this B gallon jug to fill up? Well, we have B minus Y gallons left, right? Space left. So we can take B minus Y gallons out of this one to fill up this one. So let's do it. We take B minus Y gallons out of the A jug and put it all in here, and that makes it completely filled up. So we have B gallons over here. So this is really equal to X plus Y minus B, comma B. And this only is possible if we are essentially in the complementary case. So we have that X plus Y is at least B, such that there is enough gallons in the A jug to be poured over to fill up the B jug. So these are the two kinds of cases. And of course, by symmetry, we can do also the pouring from the other jug into the first. So let's write all those out as well. So xy can actually go to x plus y comma 0. I pour everything from here to there. And this only holds if x plus y is at most a. Oh. The other possibility is where, exactly as in this case, we can only pour as a minus x gallons over from y into this particular jug. And then this one is completely filled up, and I have a few gallons left over here. So how does that look? Well, we completely fill this up to its capacity. And what is left is y minus, how much did we have to pour in here? Well, that's a minus x. And we again have a similar formula, but it now looks a little bit different. X plus y minus a. And this is only for the case where x plus y is at least a. Okay, so these are all the cases. So maybe there are some questions about this. Is this clear? That we have these different possibilities? Like when we look at these jugs, we can either empty them, filling them up, or we can pour, say, only one ball over up to the full capacity of this jug, or we can just pour everything over into, say, this jug. So those are the different cases that are now fully described by this state machine. So now we can start to prove this theorem over here. So how do we go ahead? Well, we're going to use what you have learned, like induction and invariance. So let's do it. But before actually we do this, let's take this example that we had and see how we can describe all the transitions that we just did, as far as I remember them. So we have that A equals 3, B equals 5, right? We start with empty jugs. We filled up the 5-gallon jug, right? Then we started pouring the 5-gallon jug as much as we could into the 3-gallon jug. So it's one of those rules. We got 3 and 2. Then we emptied the 3-gallon jug. We got 0 and 2. Then we did, what did we do next? Oh yeah, we poured everything into this one. So we have 2, 0 as the next state. We filled up, actually I forgot exactly what we did next, but I think we filled up the 5-gallon jug. And then we simply poured over as much as we could from the 5-gallon jug. And we got 3 and 4. And here we are. We got 4 gallons. So what we just did is fully described by this state machine. So let's now try to prove this theorem. So as I said, we're going to use induction. So you always would like to write this out if you solve your problems. What are we going to assume? Well, we assume actually that m divides a and m divides also b. That's the assumption of the theorem, and now we need to prove that m divides any result that we can achieve in this state machine. So what's the invariant that we are thinking about? Invariant is going to be, it's a predicate. And it says something like, if the state xy, if this is the state after n transitions, then we would like to conclude that m divides both x and m divides y. So this is our invariant, and we like to use this to prove our theorem. So how do we start usually, right? So we always start with the base state. Great. So let's do it. The base case is, well, we start with the all zeros, like the empty jugs. Well, and we also paid a little bit of extra attention to what we mean by division over here. And we said that all integers actually divide 0. So in particular m divides 0 and 0. So the very initial state, 0, 0, is indeed complying to this particular invariant. So let's write it out. So we have the initial state 0, 0. We know that m divides 0. And therefore we know that P0 is true. So that's great. So the inductive step. How do we start the inductive step all the time? And we will assume actually P of n, right? So let's assume that. And now we would like to prove P and then n plus 1. So what do we really want to do? We want to say, well, we know that we reached a certain state x comma y for which m divides x and m divides y. Now we would like to show that if we transition to the next state, we again have that same property, that m divides the number of gallons in both jugs once more. And then we can conclude Pn plus 1. So that's how we always proceed. So let's see whether we can write it out in a bit more formal way. Okay, so how do we go ahead? Suppose that x, y is the state after n transitions. Well, what can we conclude? Well, we have the predicate Pn, the invariant, so we know that m divides x and m divides y. And we concluded that because Pn is true. So after another transition, what happens after another transition? So we can conclude that the jugs are filled by the different types of numbers that we see here in this state machine. So let's write them out. So after another transition, each of the jugs is actually filled, are filled with, well, either if I've emptied it, say 0 jugs, 0 gallons, A, B, X, and Y I see appearing over here. And I also notice that I see X plus Y, and X plus Y minus B, and X plus Y minus A. Those are all the different number of gallons that can be in the jugs. Yes, please.
Sorry, what is in our example problem of 3 and 5?
In our example, yeah, that's a good question. So in our example problem of 3 and 5, it turns out that the only number that divides both the 3-gallon jug and the 5-gallon jug is actually 1. So in our example, we would have that m equals 1. So over here, we have that only 1 divides A as well as 1 divides B. So m equals 1 in our case. But for example, in the 3-gallon jug and the 6-gallon jug, right, we have that m equals 3. Like 3 divides 3 and 3 divides 6. So those are the two cases that we sort of look at right now. But we put it into a much more general setting, right? We abstract away from the actual numbers and use A and B as representations. Are there any other questions? Yeah. So after another transition, each of the jugs are filled with, well, either 0 gallons, if we have completely emptied them, or we have filled the first A gallon jug, or it can be B. We also notice that it can be X, of course, it can be Y, because that's the state that we are in. We can have X plus Y minus A, which appears over here, and X plus Y minus B. So these are all the different possible number of gallons. The X plus Y, oh yeah, that's also present. Is that true? Yeah, that's right. It's X plus Y, so we also have X plus Y. Actually, it's good to check that again. So we have 0, X, Y, A, B, I got those. X plus Y, and X plus Y minus B, and X plus Y minus B. Yeah. So now we can start using our assumptions. So what are they? We have that in order to prove this, right at the top over here, we assume that M divides A and M divides B. So we know that, first of all, M divides 0, of course, but we know that M divides A. We know that M divides B. We have concluded that M divides X, and also M divides Y. So if we now use some facts about divisibility on your handout, which we will not prove now, but I think most of them will be on your problem set, actually. We can conclude that also a linear combination of A, B, X, and Y will be divisible by M. In particular, M will divide X plus Y, M will divide X plus Y minus A, and also X plus Y minus B. So we will conclude that M actually divides any possible result. So divides any of the above. And now we're done. Why is that? Because we have shown now that after the next transition, after we have reached x, y after n steps, then in our n plus 1th step, all that we can achieve is divisible by m. So that's exactly the invariant. So we conclude that Pn plus 1 is true. And so now we're done. Are there any questions about this proof? So this is like the standard technique that we try to use all the time here in this class. We will use it in all the other areas as well, in graph theory in particular. Especially in number theory, we will also use it, especially in this class. Okay, so let's apply this theorem. Let's think about this movie that we saw, this, Die Hard number 3. Die Hard number 4 came out. And then the cast got stuck in Die Hard number 5. That was a problem because the rumors were that in Die Hard number 5 they had like a 33-gallon jug. That's a lot. And a 55-gallon jug. So Bruce has been training his muscles, because you can imagine those are pretty heavy, so if you want to pour one into the other, my goodness. So, but the question is he training the right muscles? So can we apply this theorem now and show that, I should tell you what is the problem. Well, again, he has to get, say, 4 gallons out of these 2 jugs. So is that possible? It's not. I see someone shaking his head. Do you want to explain why?
A and B are both divisible by 11.
Yeah.
So any other configuration will also have to be divisible by 11.
Yeah.
And 4 is not divisible by 11.
Exactly. So 4 is not divisible by 11, so the whole cast got blown up in Die Hard number 5. And so we have no Die Hard number 6 as well. Okay, so now all of this stuff actually helps us to define a new concept as well. So let's do that. I'll put it up here. We will use the terminology GCD of A and B as being the greatest common divisor of A and B. So, for example, if we are looking at A equals 3 and B equals 5, well, then the GCD of 3 and 5 is actually equal to 1. There's no other larger integer that divides both 3 and 5. And other examples are, for example, if we have the GCD of, say, 52 and 44, well, what's this equal to? Well, this actually is 4 times 13. This is 4 times 11. So 4 divides both this and both this one, but nothing larger can divide both of those. So we have that this is equal to 4. We will have a separate definition that talks about this very special case where two numbers, if you look at their greatest common divisor, when that greatest common divisor is equal to 1, we actually define those two numbers to be relatively prime to one another. So let's put that out over here. So that's another definition. We say that A and B are relatively prime if their greatest common divisor is actually equal to 1. Now, today we will not really use this definition so much, but it's actually very important, and we'll come back to this next lecture. So, if we now look at this particular theorem over here, can we see a nice corollary of this? Like a result, if you think about this greatest common divisor, well, the greatest common divisor of A and B divides both A and B. So the greatest common divisor of A and B will divide any result that we can generate by playing this game with the jugs. So the corollary here is that the GCD of A and B divides any result. Okay, so that's really cool. So this already tells us quite a bit about this game that we have here. So now what we would like to do is to find out what exactly can be reached. We have a property that we have shown here, but what else can we do here? Now it turns out that we can say much more, and we would like to prove the following theorem to make to analyze this whole thing much better. I don't think I need the state machine anymore, so let's take that off. The theorem that we would like to prove is that any linear combination of the, let's change this into the 3 and 5 again, any linear combination of 3 and 5 I can make with these 3 and a 5 gallon jug. So let's write it out. So any linear combination L, which we write as some integer s times A plus some integer t times B. So any linear combination of A and B with, well, of course, the number of gallons should fit the largest jug. So with 0 is at most L, is at most B, can be reached. So this theorem we would like to prove now. And in order to do that, we would like to already think about some kind of a property that we have. So when we talk about linear combinations, the S and the T can be negative or positive. We really don't care. So for example, we could have like, I don't know, minus 2 times, so for example, 4 is equal to minus 2 times 3 plus, actually, is that true? Yeah, plus 2 times 5. So here we have S to be equal to minus 2, and T is equal to 2. And of course, A is equal to 3, right? And B equals to 5, is equal to 5. So 4 is a linear combination of these two. And according to the theorem, we can create that number of gallons in this jug. And we already saw that because we did it. But for our theorem, in order to prove this, we really would like S to be positive. So how can we do that? Does anybody have an idea what we could do? Oh, please.
Does this assume that B is greater than A?
Yeah, we have still that A is supposed to be. We will assume that throughout the whole lecture. Thanks. So in order to prove this, we really would like to have S to be positive. So let's just play around a little bit with linear combinations to get a little bit of a feeling for that. How could we write 4 differently as a linear combination of 3 and 5, such that we have actually a positive number over here? Does anybody see another way to see that? Yeah, that's true. 3 times 3 minus 5. So, and how did we do that? Well, we can just add, say, 5 times 3 to this one, and then subtract the same again, minus 3 times 5 over here. And if we add those things together, you will see 5 minus 2 is 3 times 3, as you said. And we have minus 3 plus 2 is actually minus 1 times 5. And this will be a different linear combination of 4. So what we can do here, we can sort of play around and make this S over here, which we now say call S prime, is positive. Actually, it's larger than 0. So let's start a proof for this theorem. It's pretty amazing to me, actually, that you can do so much with a game like this and see so much happening. So let's figure out how this works. Okay. So let's first formalize this particular trick over here. And how do we go ahead with it? Well, notice that we can rewrite L, which is equal to S times A plus T times B, as, you know, we can just add a multiple of B over here, M times B, say, times A, and we can subtract that same amount over here, minus M times A times B. So, do you see what I did over here? I have added M times B times A and subtracted M times A times B. And we did something similar over here, not exactly the same, right? But that's what we did. And you can imagine that we can choose M such that S plus M times B will be larger than 0. We can do that. So essentially this proves to us that there exists an S prime and also a T prime such that L can be rewritten as a linear combination S prime times A plus T prime times B, but now with the extra property that S prime is actually positive. Now this is really important because we're going to create an algorithm of playing with those jugs that can achieve this particular linear combination. And that's how we're going to prove this theorem. So let's assume that 0 is less than L, is less than B. I know that we, in the theorem, we also consider the cases L equals 0 and L equals B, but those are obvious, right? I can either empty the jugs or just fill up the bigger one. So we will consider just this case. All right, so what's the algorithm going to do for us? The algorithm is going to repeatedly fill and pour out jugs in a very special way. And miraculously, we will be able to get the desired linear combination every single time. And of course, we're going to use induction again to prove this property. Okay, so how does the algorithm work? Well, to obtain L gallons, we are going to repeat S prime times, which is the number that we have over here, the following algorithm. We first of all, we will fill the A jug. That's one. After we have done this, we're going to pour this into the B jug. So how do we go ahead? We pour this into the B jug. And when this B jug becomes full, we're going to pour it out. So let's write it out. So when it becomes full, we will actually empty it out. And we will continue pouring the A jug into the B jug. So we'll continue this process. So let's take an example to see how that works. So we keep on doing this until the A jug is actually empty. So let's take an example. So let's see. Let's do that over here. Actually, we can do it with the tennis balls too. Let's do that first. See how that works. So, essentially, in order to get 4 gallons, we just fill up the 3-gallon jug. We empty it all in here. We fill it up again. We pour in as much as we can. That's it. We have to empty this one. Oops. We have to keep on pouring. Put this in here. Fill this one up. And then pour it over into the 5-gallon jug. And now we got 4 gallons over here. So what did we do? So let's write it out. So for our special linear combination over here, we have that 4 equals 3 times 3 minus 1 times 5. So we need to repeat this process 3 times. So let's do that. In our first loop, we will do the following. We start with the start state, the pair 0, 0. We're going to fill up the very first jug all the way up to its capacity, 3. And we pour it all over into the B jug. What happens in the second loop? The second loop, we again fill up the A jug. So we start with 0, 3. We fill it up, and we get 3, 3, the pair 3, 3. we pour everything in here as much as we can. That gives us 1,5. Only 2 gallons are poured into the bigger gallon. We empty the bigger gallon, the bigger jug. We get 1, 0. And we keep on pouring, and we get 0, 1. So now in the third loop, and that's where we should get the 4 gallons, we start off with 0, 1. We fill up the A jug. We pour everything over into the bigger jug, and we get 0,4. And that's the end result. So this algorithm seems to work for this particular example. Of course, you would like to prove it for the general situation. So how do we do it? Well, we're going to just analyze the algorithm in the following way. We can notice that in this algorithm, we fill up S prime times the A jug, and we essentially pour everything out into the B jugs, and we sometimes empty the B jug. So let's try to think about this a little bit and see how we could try to formalize this. So let's write it out. We have filled the A gallon jug S prime times. We also know that the B jug has been emptied a certain number of times. So let's just assume, suppose that the B jug is actually emptied, say, U times. I do not know how many times, but I just say, well, let's assume it's U times, and then try to figure out whether we can find some algebraic expression. So at the very end of the algorithm, let R be what is in the B jug. So let R be the remainder in the B gallon jug. So now we can continue. We know if R is what is left in the B gallon jug, well, we know already some property of it. Actually, let's put it on the next board. We know that 0 is at most R and at most B, because that's what's left in the B gallon jug, right? So we know these bounds. We have assumed that 0 is less than L is less than B, which we put over there. We know that R must be equal to what kind of linear combination of S prime and U. So, well, we have been filling the A jug S prime times. So this is what we added in water to the whole system, you can say, S prime times A. And we poured out water. Well, we did that U times from the B gallon jug. So we poured out U times B gallons. So this is the remainder that is left in this bigger jug, right? So are there any questions about this? So, okay. So we also know that L is equal to S prime times A plus T prime times B. And this is the linear combination that we would try to prove of, that it is left at the very end. So what we want to show is that R equals L. So how do we do that now? Well, we're going to show that that R can be expressed in L in a special way. So let's have a look. So these are all tricks in the sense that I'm giving you this proof, but how do you come up with this yourself? Sometimes you play a lot with these kinds of things, and you get a feeling of what kind of sort of pattern exists and what kind of intuition you need in order to write down a proof like this. So let's rewrite this. I'm going to add t prime times b, and I'm going to subtract it again. So I have s prime times a plus t prime times b. I subtract it again, and I still have this amount left over here. So what is this equal to? Well, this part is equal to L. So this is equal to L minus, and I have a multiple of b, which is t prime plus u times b. Now this is very interesting. Does anybody see how we could continue here? So we have r expressed as L minus a multiple of b. And I also know that L is in this range. I also know that R is in this range. So that's kind of interesting, right? So how can that be? What should be the case here? Does anybody see what kind of property t prime plus u must have in order to make that happen? So let's have a look here. We have L. It's in this range. So let's just draw an axis. So we have 0, we have b, and somehow in this range we have L. Now if I subtract like actually b or something more than b, or I add more than b, I will jump out of this range and I go somewhere over here, or I go somewhere over there. Right? So if I suppose L is over here, then L minus b would be over here, which would be negative. Or if I add b, it will be over here, which would be more than b. Now, we know that this is equal to r, but r is in this range. So that's not really possible. So let's write it out. So if t prime plus u is unequal to 0, so I actually really subtract or add a multiple of b, then I know that r is either smaller than 0 or r is larger than b. Now we know that that cannot be the case, so we can conclude that t prime plus u equals 0. Now that implies that t prime equals minus u, or maybe the other way around, because that's easier to see what's happening. So u equals minus t prime. If we plug that in here, well, we get exactly the same expression. You see? Minus t prime is equal to plus t prime, and we get the exact same linear combination. So we conclude that r equals L, and now we're done. Why is that? Well, we have shown that the very last number of gallons that is left after this procedure, after this algorithm, is actually exactly equal to the linear combination that we wanted to achieve. So now we got the proof for this theorem that tells us that that any linear combination is actually of A and B can actually be reached by pouring gallons over and back and emptying and filling those jugs. All right, let's continue. So there was a question over here that I would like to address. So maybe I did not make so clear what the S prime and the T prime is over here. And in this proof, we started off with this linear combination. I would like to have an algorithm of pouring that creates L gallons in, say, the bigger jug. So in order to do that, I want to find, say, a linear combination that makes this L such that this S prime is an integer, a positive integer. Why do I want to have a positive integer? Because in this algorithm, I'm going to repeat something S prime times. If S prime is negative, I cannot do it, right? So S prime has to be a positive integer. In order to create such a positive integer, I can just add like 1,000 times b times a and subtract 1,000 times a times b. That's okay. I can just add a lot. And if I add enough, I can make s plus n times b positive. Even if s is, say, minus 100, well, if I add 1,000 times 5, I will get a positive number. So that's sort of the reason in this proof that we want to rewrite the linear combination into a new one, such that this S prime is positive. And if we have S prime positive, then we can actually talk about this algorithm, because we can only repeat something S prime times if S prime is, say, 1 or 2 or 3 or something positive. All right. So let's talk about the next part. So we have proved 2 theorems, but in the end we would like to have a characterization of the greatest common divisor. That's the goal of this lecture. So let's do it. In order to do this, let's first of all look at our 5-gallon and 3-gallon example. We know that the greatest common divisor is equal to 1. We know that 1 can be rewritten as a linear combination as 2 times 3 minus 1 times 5. So that means that according to the theorem that we have up here, we can actually make exactly 1 gallons in one of these jugs. So that means that we can also have any multiple of those. So we can reach any multiple of 1. That's very special. So in this particular case, we know that any multiple of 1, any number of gallons can be reached. So can we sort of generalize this a little bit by using the greatest common divisor? So the greatest common divisor of 3 and 5 is equal to 1. And we have shown that the greatest common divisor divides any result. Can we say something more? Can we say that the greatest common divisor can be maybe written as a linear combination of this type over there? And that's how we are going to proceed now. So let's talk about a very special algorithm, which is called Euclid's algorithm. And I think in the book it's also called the pulverizer. And you will have a problem on this, just to see how that works and to really understand it. So let's explain what we want here. So first of all, we know that for any b and a, there exists a unique quotient and remainder r. So let's write it out. There exists a unique q, which we will call the quotient, and r, we'll call this the remainder. Such that b equals q times a plus r, with the property that 0 is at least r and at most a. So we're not going to prove this statement. It's actually like a theorem, right? But let's just assume it for now, and in the book you can read about it. We're going to use this to prove the following lemma, that we will need to give a characterization of the greatest common divisor as a linear combination of integers. Before I forget, we will denote this remainder as rem of b comma a, and this is the notation that we use in this lecture. So what's the lemma? The lemma is that the greatest common divisor of a and b is equal to the greatest common divisor of the remainder of b and a with a. So what did we do? Let's give an example to see how this works. For example, let's take, actually let's do it on this whiteboard. For example, let's see whether we can use this to calculate the greatest common divisor of 105 and 224. So how can we go ahead? Well, according to this lemma, we can rewrite this as the greatest common divisor of first the remainder of 224 after dividing out as many multiples of 105 as possible, and 105. So what are we going to use here? We're going to use that 224 is actually equal to 2 times 105 plus 14. So we have the GCD of 14 and 105. Now, why can I do this? Well, I'm essentially just subtracting like 2 times 105 from 224. Well, the greatest common divisor that divides 105 and 224 also divides 105 and a linear combination of 105 and 224. That's essentially what we are using. And that's actually stated in this lemma, and that's what we would like to prove. So let's continue this process and do the same trick once more. So we can say that we can rewrite this as the greatest common divisor of, well, the remainder of 105 after taking out as many multiples of 14 as possible, and 14. So what are we going to use over here? We are going to use that 105 is equal to 7 times 14 plus 7. So this is the greatest common divisor of 7 and 14. Now if you just continue this process, we can see that this is equal to the greatest common divisor, again, of the remainder of now 14 after dividing out as many multiples of 7 with 7. Now, this is equal to 0, 7. Why is that? Because 14 is equal to 2 times 7 plus 0. So 0 is the remainder after dividing out 7 as many possible times as possible. Okay, so we have the greatest common divisor of 0 and 7. What's the largest integer that can divide both 0 and 7? Well, any integer can divide 0. So we know that this is equal to 7. So essentially what we have done here, we have repeatedly used this particular lemma to compute, in the end, the greatest common divisor of 105 and 224. And we have been very methodological. We used a specific method. We used the lemma, and we worked it out. We used the lemma again, and we just plugged in the actual numbers. Used the lemma again, plugged in the actual numbers, and so on. And this is what is called Euclid's algorithm. And in the book it's also called pulverizer, and it has, I think, a few other names. But I like this one. So this is an example of Euclid's algorithm. So now let's have a look whether we can prove this particular lemma. And actually, I will, yep, we're going to prove this lemma. Okay, so how do we do the proof? Well, first of all, we know that if, well, how do we do this? We would like to prove that if if n divides a and b, in particular the greatest common divisor divides a and b, we would like to show that it's dividing also the remainder of b after dividing out a and a itself. If we can show that, then we know that the greatest common divisor of this thing is at least what we have over here. So I said a lot right now. So let's try to write it out a little bit. So suppose that m is any divisor of a, and at the same time m also divides b. Well, then I know that m also divides b minus, say, the quotient q that we had over here times a, and this is actually equal to the remainder of b and a. Now we also know that m divides a. So what did we show here? We showed that if m divides a and m divides b, then m also divides the remainder of b and a, and m divides a. So what does this prove? Well, it proves that, in particular, the greatest common divisor over here divides this one. That's interesting. It essentially means that we have shown this inequality. Because if this one divides this, well, that means that this number over here must be at least what we have over here. Okay, so let's continue. We consider two cases. If the remainder of b and a is unequal to 0, well, what can we say now? We can say that if I know that m divides this remainder of b and a, which can be rewritten as b minus q times a, and I also know that if I also know that m divides a, then this actually implies the reverse of this statement, that m divides a and m divides b. Now, why is that? Well, we're actually using the fact that if m divides b minus q times a and m divides a, then m also divides any linear combination of these two, in particular this plus q times a, which is b. M divides b. So maybe I'm going a little bit fast here, I notice. This also has to do with all the, at your handout you see a few facts on divisibility, and in particular item number 3 talks about the fact that I'm using here. If a divides b on your handout and a divides c, then I know that a divides any linear combination of b and c. So that's essentially what I'm using here repeatedly. Okay. So let's look at the other case. If the remainder is equal to 0, well then I actually know that b minus q times a is equal to 0. Well, if I know that m divides a, well, then since 0 equals b minus q times a, I know that b equals q times a. So if m divides a, I also know that m divides b. So this is one argument. This is another one. And these are the 3 arguments that now show that anything that divides these two also divides a and b. So now we have the reverse argument, right? So this greatest common divisor divides this one here and this one. And we just proved that it divides a and b, and so it must divide the greatest common divisor of a and b. So now we have shown the other inequality, and this proves equality. So you should definitely look this up in your lecture notes. So now we can finally prove this beautiful theorem that will help us to characterize actually let me put this over here. So the final theorem that we prove here is that the greatest common divisor of A and B is actually a linear combination of A and B. So we're going to use this algorithm that we have over here, Euclid's algorithm, and we are going to do a proof, again by induction, and we use an invariant. So we use a similar kind of strategy, of course. The invariant that we're going to use says, well, if Euclid's algorithm reaches the greatest common divisor of x and y, so for example, it reaches, say, 7 or 14 and 105, for example, then, say, after n steps, then both x and y are linear combinations of A and B. So then x and y are linear combinations of A and B. And at the same time, we also know that the greatest common divisor of A and B is equal to the greatest common divisor of x and y. So this is my invariant, and the way I will go ahead is to simply do what we do always in these situations. So we start with the base case, and we can immediately see that after 0 steps, in the Euclidean algorithm, I've done absolutely nothing. So obviously, after 0 steps,
you know I got it. I pull up, I come round, make my rounds, it's my town. You know I got it. Hey, when I'm round, they now. What's up now? This touchdown like. Hey, niggas from city be hating them niggas, don't show me no love. Hey, it is what it is, cause I'm brushing my shoulders, walk off with a shrug. Hey, this shit is a dub. Hey, this shit is a dubsy. Hey, why am I all in my feelings when I got these people that love me? Hey, I cannot feel none you niggas, I only feel one that's above me. Hey, come for me quick and I promise my niggas will make it get ugly. Hey, this shit is a dub. Hey, this shit is a dubsy. Hey, why am I all in my feelings when I got these people that love me? You know I got it. I pull up, I come round, make my rounds, it's my town. You know I got it. Hey, when I'm round, they now. What's up now? This touchdown. You know I got it. I pull up, I come round, make my rounds, it's my town. You know I got it. Hey, when I'm round, they now. What's up now? This
whatever
touchdown.
You want, then I'm with it. Ay. Down for the cause, I'm committed. Ay. These niggas be causing the scene. Ay. I'm just perfecting the image. Ay. Now the game is a scrimmage. Ay. I just been pushing the limits. Ay. Don't got no on my team. Ay. All of my niggas is killers. All of my niggas is squad. Really been down for the cause. No fake friends. Can't say the same about y'all. I'm minding my business and staying committed. I'm treating this like a job. I'm running the muck and I'm causing the clinic. I don't do this for applause. Yeah,
you know I got it. I pull up, I come round, make my rounds, it's my town. You know I got it. Hey, when I'm round, they now. What's up now? This touchdown. You know I got it. I pull up, I come round, make my rounds, it's my town. You know I got it. Hey, when I'm round, they now. What's up now? This touchdown.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So let's get ready. If good, you should receive some handouts. So the TAs are walking around. So you should slowly get those. This is the second lecture on number theory, and we're going to cover a lot of stuff. And actually, we're going to start with encryption, which is an application of number theory, and we will take that as a theme throughout the whole lecture. And so in this way, you can see how useful number theory is. Now, encryption, yeah, what is it? So let's first talk about that a little bit. Maybe some of you have heard about it, but cryptology in general is the art of hiding information, and encryption is a very useful tool. I'll only give a very high-level overview. I mean, if you really want to know more about this, you should do a class in crypto or practical security. So what's encryption? The idea is usually that beforehand, we're going to share a whole bunch of keys. So keys are exchanged between a receiver and a sender. And the whole idea is that if I want to transmit like a message to one of you, well, there could be someone in the middle who wants to intercept my message and wants to find out what I'm saying. So I do not like this. And in order to avoid it, I will use encryption, which is some kind of algorithm that actually transforms my message M, my plain message, by using some kind of algorithm E, some encryption algorithm. It can be a function as well, that uses the keys in order to transform this into an encryption, which we call M prime here. So the plain text has in the clear all the information that I want to convey to one of you, for example, and M prime is somehow a complete mixture of bits out of which I'm not able to distill any information about the plain text. So encryption is a very special kind of thing, and we're not going to talk about the precise definitions here, but we just take the idea into this lecture. Now, decryption is transforming the ciphertext back into the plain text. So we will start with the encryption, M prime, and we have some kind of decryption algorithm. And again, we can make use of the keys that we exchanged, and we transform it back into the plain message. So only if I know the keys, I can actually transform back the encrypted version into the plain version. So, well, in encryption schemes, we like both these algorithms to be really efficient. And the security of such a scheme, well, the first kind of intuition that we can get is that, well, if I'm a man in the middle, somewhere intercepting like an encrypted message, M prime, I should not be able to get any information about M if I have no knowledge about those keys. So this is the example that we're going to take throughout this whole lecture. So let's start with a first possible scheme. Turing, who lived like around 1936, he was 24 years old, and he lived till about, actually, I think he was about 54 when he died. In any case, Turing was the one who first originally proposed to use number theory in cryptography. And before he joined the British Army, before the Second World War, he actually proposed a scheme, but it got never published. So here in this class, we are going to try to think about what he could have thought about. So we will have a first scheme, which we will call Turing's code, version number 1. And the whole idea is that we are going to translate a message, first of all, into a prime number, because we want to use numbers. You're here in number theory class, so we want to use some tricks with numbers in order to encrypt it. So let's do this. So for example, let's take the word victory. We can map this into an integer. For example, we could say, well, m is 22, where I map v to, because I know that v is the 22nd letter in the alphabet, I just start with 22. I is the 9th letter in the alphabet, so I append 09. C is the 3rd letter in the alphabet, I append 3, 03. I continue like this. And in the end, over here, I have mapped y to the 25th letter. Because it's the 25th letter of the alphabet, I write 25. It turns out I can just add a couple of digits more if I specially compute those. In this case, I could add 13. And then it changes into a prime number. Now, we're not going to talk about why this is and how this can be done and so on, but it turns out that the prime numbers are densely distributed over the integers, and it is really possible to, just with a few extra digits, by selecting them in a smart way, to actually create a prime number and also verify that it is a prime number very efficiently. So it's very easy to compute, to translate such a word into a prime number. So this is how it all starts. And just like in an encryption scheme, beforehand, we are going to exchange a key. So we exchange a secret prime in this example, which we call k. And the encryption is very simple. We are just going to multiply m with k. Now you may wonder, why is this such a fantastic idea? But let's bear with me. So m is this first prime number, and we multiply it by a second prime number, and that's going to be our encryption. Now, how do we decrypt? That seems to be pretty straightforward, right? How do we do it? We start off with m prime. I know we have exchanged the secret prime k, so if I receive from you this message, this encrypted message, well, I know the key k, so I just divide it by k, well, which is mk divided by k, and I get m. So that's pretty straightforward. Now, it turns out, actually, and I will write it up here because we need it later, that it's not so trivial to actually just give an m prime to figure out what m is, or k. M prime is the product of two very large prime numbers, and that turns out to be a really hard problem. Up to now, nobody has really been able to get a really efficient algorithm to solve that. So we may think this is secure. So let me write it down. It's hard to factor a product of two large primes. You will actually need this also when we come to the final encryption scheme, RSA, that we will discuss, which is widely used. But something is wrong here, though. This seems to be too simple, right? So what can we do if we have, like, say, suppose I intercept two encrypted messages? What can I do? So suppose I have a first message, m prime 1, which is the product of a first plain message times the key k. And I have a second message that is encrypted by using the same key, which is m2 times k. Does anybody have an idea what I could do here? Yeah,
find the GCD. That would be really
yeah, you could find the GCD of m1 prime and m2 prime. I've intercepted those two. Now M1 is a prime number, K is a prime number, M2 is a prime number, K is a prime number here also, right? So they're all relatively prime towards one another. The GCD of these two, well, the greatest common divisor is K. So just by calculating the GCD of the two encrypted messages, I will be able to figure out what K is, the key. So that's, well, if I know the key, then I can do the decryption of any ciphertext, any encryption of a message that I can intercept. So this is not secure. So how can we change this? Can we create a different kind of encryption scheme? Let's do something much more difficult, and then we will get into modular arithmetic and things like that. So let's do this. So Turing's code version number 2, we try to do something much more complicated than just multiplying by prime. So let's do the following. So beforehand, we are going to exchange not only a secret prime K, but we will also exchange a public prime. So we exchange, by public we mean that anybody can see this prime, it's common knowledge, a public prime P, and also a secret prime K. Well, let's see whether this would work. We have an encryption. Well, we're going to start out exactly the same way. First of all, I should tell you how a message is represented. A message is going to be represented as a number M in the range from 0, 1, all the way to P minus 1. And we will compute the encryption as follows. M is going to be the remainder of M times K after dividing out as many multiples of P as possible. So notice we do kind of the same thing. We just multiply by K, but now we just take the remainder after taking out as many multiples of P. Well, let's see whether we can do the decryption. It seems to be like a next level of complexity, so maybe that will help us here, right? So how would we do decryption? Well, somehow we would like to divide by K, but we cannot really do that, right? This does not make any sense. So the decryption, we have no idea at this point how to do this. And now we can get into modular arithmetic because it turns out that we can sort of divide by K. There exists what we call multiplicative inverse of K modulo P, and I will explain all those terminology to you. And then we will be able to take M prime and transform it back to M. So we will be able to get a lot of this machinery going. So let's find out how this works. So first of all, last time we saw that we defined A and B to be relatively prime. So let me repeat that. So A and B are relatively prime. If and only if, that's how we defined it, if the GCD of A and B is equal to 1. And in last lecture and in the recitation you got a different proof, I think. We proved that actually the GCD of A and B is equal to the smallest positive linear combination of A and B. So that means that 1 in particular is a linear combination of A and B. So there exists integers S and T such that S times A plus T times B equals 1. It turns out that we can also go the other way around, because if I can write 1 as a linear combination of A and B, well, I cannot get much lower than that, right? So that's really the smallest possible that I can achieve. So the GCD must be equal to 1. So this is a property that we will be using. From this property, we can already figure out an interesting property. So suppose we have a linear combination that looks like this. Then you can imagine that that S times A is equal to 1 plus or minus some linear multiple of B. So it's sort of S times A is sort of equal to 1, you can say, up to a multiple of B. So you can see A sort of as an inverse of S, because S times A is equal to 1, sort of. So this is what we're going to use, this kind of feeling. And in order to do that, we are going to define congruency. So that's the first definition for this lecture. We say X is congruent to Y modulo N, if which we denote as follows: X with 3 bars, Y in between brackets mod N. And we say that this is the case if N divides the difference between X and Y. So let's have a look at some examples. So let's take 31, and I'd like to show to you that this is congruent to 16 modulo, between brackets, 5. Why is this? Well, I take the difference between 31 and 16, which is 15, and I know that 15 is 3 times 5, so 5 divides this difference, and then by the definition, we can write it like this, and we say, that's the definition, 31 is congruent to 16 modulo 5. Another example is, we will stick with this example. It's pretty clear. So once we have defined this, we can continue and talk about this inverse that I was talking about. So we like to sort of explain in this encryption scheme how we can divide by k. Actually, we would like to multiply by an inverse of k, and we're going to use this framework. So we'll have a new definition that talks about the multiplicative inverse. So it's a new concept, and we'll give a couple of examples. So the multiplicative inverse of X modulo N is a number which we denote by X and then minus 1 on top of here. It's a number in the interval 0, 1, all the way up to n minus 1, such that X times X inverse, so X times its multiplicative inverse, is congruent to 1 modulo N. So this is the definition for a multiplicative inverse. So let's have some examples. So let's do that over here. For example, we have that 2 times 3, which equals 6, right, is equal to 1 modulo 5. Why is this? Well, 6 minus 1 is divisible by 5, so I know that this is congruent to 1 modulo 5. So what does this mean? Well, we can say that 2 is actually equal to the multiplicative inverse of 3 modulo 5. We can also say that, that 3 is the multiplicative inverse of 2 modulo 5. Let's have another example, just to make it a little bit more clear. We know that 5 times 5 equals 25, and this is congruent to 1 modulo 6, because 25 is 1 plus 4 times 6. So now we see something funny happening, because 5 is actually equal to its own multiplicative inverse, modulo 6. So are there any questions about these concepts? Because these are really basic for the whole lecture, and this is what you really need to understand if you do all the problem sets as well. Are there any questions? So now we can actually start talking about this second version of the Turing code that we invented. Let's have a look at this remainder. So let's write it out again. The remainder of m times k after dividing out as many multiples of p, well, we know that this is congruent to m times k modulo p. So why is this? Well, we just apply the definition over here. We take the difference between those two. So here we have the remainder of m times k after dividing out as many multiples of p. And if we subtract that from m times k, well, then we have something that is a multiple of p, because that's what we divided out. So the difference is a multiple of p. So that means that p divides the difference, and that's the definition of saying that this remainder is congruent to mk modulo p. So this is kind of interesting, because now we can rewrite over there, well, not really rewrite, but we can use this to analyze the encryption over here. So m prime is equal to this remainder, and we get a beautiful equation. We see that the encryption is congruent to the plain message times the key modulo p. So how do I do decryption? I can use the multiplicative inverse of k, right? So then I can divide k out. So let's write this out as well. So suppose I have a multiplicative inverse, k to the power minus 1, that is congruent to 1 modulo p. Why do I do this? Why am I writing this out? Because we will see that it is not always possible to have a multiplicative inverse. That's going to be really a big problem. And that's where all these other functions come in, the Euler-Totient function and Euler's theorem and so on. So it's not really always the case. We'll give an example in a moment. But suppose that we have a multiplicative inverse, modulo p. Well, then I'm able to easily compute, well, I take m prime, I multiply it with k inverse. Well, this is, I'm substituting for m prime m times k times k inverse. I still have this left. Now I can say that this is equal to 1 modulo p. So this is equal, or is congruent to m modulo p. So now we see how we can do decryption. We simply use the multiplicative inverse of k, and as in the first Turing code, we are able to somehow divide out, so where did I have it? To divide out k. I did it very differently. I have a very different mathematical structure, but the idea is essentially the same. I have a multiplicative inverse of k, and if I multiply this with the encryption, I will get the plain message, modulo p. So am I finished now is the question. Well, I know that m is in the range of 0, 1, all the way up to p minus 1. So this means that I can also rewrite m as, and I use a similar trick as what I did over here. I can rewrite m as the remainder of m prime times k inverse after dividing out as many copies of p as possible. So what we did here is to first prove that the difference between those two is a multiple of p. That's essentially what congruent modulo p means. That's the definition. So now that I know that the difference is a multiple of p, And if I know that m is actually in this range up to p minus 1, I can use what we learned last lecture and what the book was talking about, that the definition of the remainder of m prime times k inverse, this thing, after finding out as many copies of p, is exactly this plain message m. Okay, so now we have the decryption. So this is decryption. And that sounds great. So now, of course, we are wondering, well, if we can do this, can we also attack this scheme, right? Can we do something bad with it? Well, it can be used to break this code, but in a slightly more complicated way. So let's see where I put that. Right, so what we're going to use now, so when we talk about security and so on, you can think of all kinds of ways to break an encryption scheme. So we started out with, in the first version, well, what if I just know the encryption and then, well, I cannot know anything about the plain text simply because I know that it's very hard to factor a product of two large primes. Then I said, but suppose I know a little bit more as an adversary. Suppose I have a plain message together with a encrypted message. Well, then I could do this GCD trick and figure out and break the scheme. And now we're going to do something similar, and we say, well, suppose that I do not know two encryptions, but I know a plain message and a corresponding encrypted message. So if I know such a pair, which is, I mean, in practice, such type of information will be leaked, then in this case I can break it. So we call this the known plain text attack. And it assumes that we know, as an adversary, I know a message, a plain message, M, and also an encryption of this message, M prime. And M prime, according to this scheme, is the remainder of M times K after dividing out as many multiples of P as possible. Now we saw, now suppose I know these two, I'm going to show to you how to break it. So let's have a look. The encryption M prime here is congruent to M times K modulo P. We just proved it over here. And what do we know? We know that P is a public prime. I know P. Since it's a prime, I know that the GCD of M and P equals 1. So these two are relatively prime. So now if they're relatively prime, and that's what we wrote up here, we know that there exists this linear combination of, in this case, M and P, that is equal to 1. And in this way, we can figure out how to compute the inverse, the multiplicative inverse of M. So that's what we're going to do. So we can compute the multiplicative inverse such that M times M inverse is congruent to 1 modulo P. So now we can do the next step. So well, what could I do next? So let's see, if I have such an inverse, then I can take my encrypted message that I have as an attacker, which is M prime. I know M, and since P was public, I can compute this multiplicative inverse, so I can just compute this product, and I know that this is actually equal to, well, K times M inverse. This is again equal to, congruent to 1 modulo P. So this is equal to K modulo P. So now all of a sudden, I know K modulo P, because I know those two. So if I know K, I can compute its multiplicative inverse. So I can compute K inverse modulo P. And if I know K inverse, again, I can use it to decrypt any other encrypted message that I receive. So for all future encrypted messages, I do not need anymore the plain messages. I have already used, just by using one plain message encryption pair, I have been able to compute the secret key and the whole scheme is broken. So security is kind of an interesting science. We can always think of more tricks to break schemes or other assumptions that we haven't thought about before. So now let's talk about, so what did we do here? We have been talking about encryption, these two schemes. We talked about modular arithmetic, talked about congruence, and also the multiplicative inverse. And we showed how to use that to break Turing's code version number 2. So we need something much more fundamental in order to create a scheme that is really secure. And that's what we're going to do now. We're going to start off with Euler's totient function and then prove a related theorem. And with that, we will be able to actually explain the RSA algorithm, which is a famous algorithm invented here at MIT in 1977 by Rivest, Shamir, and Edelman. And they actually also got the Turing Award for this a few years ago. And it's widely used in practice. But we will be able to actually explain this algorithm with just this fundamental piece of number theory. So that's really exciting. So let's do this. So we're going to first define Euler's totient function. And it's related to this multiplicative inverse. This function is denoted by phi of n, and it denotes the number of integers in 1, 2, 3, all the way up to n minus 1 that are relatively prime to n. So, well, this just drops out of the air, you may think, but yeah, this is a fundamental quantity, and Euler's theorem is what we will try to prove next. But let's give a couple of examples about this, just to see how it works. So for example, let's take n to be equal to 12. What would be the value of Euler's totient function evaluated for 12? So if you take 12, we have the following numbers to consider: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So now let's have a look. We want to count the integers that are relatively prime to 12. Well, 1 is relatively prime to 12. Why is that? Because the GCD of 12 and 1 is equal to 1, and that's the definition of being relatively prime. So this is a good number. The GCD of 12 and 2, well, both are divisible by 2, and so they're not relatively prime because the GCD is at least 2, in this case equal to 2. 3 also divides 12. 4 divides 12. 5 is relatively prime with respect to 12. 6 actually is dividing 12 as well. 7 is relatively prime. And 11 over here as well. And all the others have a greatest common divisor that is larger than 1. So here we see that the Euler-Tauschig function evaluated in 12 is equal to 4. There are 1, 2, 3, 4 integers that are relatively prime. Okay, so let's have a different one, say n equals 15. It's a little bit different, because here you may think this is kind of coincidental that 1, 5, 7, and 11 are actually also primes. But for 15, it looks a little bit different. So let's write out all the numbers. Again, let's have a look. Well, 1 has greatest common divisor equal to 1 with respect to 15. 2, well, is also relatively prime with respect to 15. 3 is dividing 15. 4, yeah, 4 and 15 have greatest common divisor equal to 1. So that's relatively prime. 5 is not. 6 is not. 7 is relatively prime. 8 again. This is only divisible by power of 2. And this has no power of 2 in it. 9, 10 this one is divisible by 5, divisible by 3. 11 is again relatively prime. And then we have 13 is relatively prime as well. And 14 as well, because this is 2 times 7, and this is 3 times 5. So how many do we see now? 1, 2, 3, 4, 5, 6, 7, 8. So the Euler-Tauschig function evaluated in 15 is actually equal to 8. Now, it turns out that this function has really nice properties, and you can easily calculate if you know if you know the decomposition of n into its primes and powers of primes. You can easily compute this number, phi of n. Now, you will be able to find this in the book. You should read it. And also the problem set talks about this. But for now, let's just talk about this as an abstract notion, because that's all that we will use in this lecture. But you will have a few exercises that talk about computing this kind of stuff. Okay. So let's talk about the Euler-Tauschig function and Euler's theorem. So let me use this blackboard. Now this is really an exciting theorem, and it's a little bit hard to prove. That's why we will need a little bit more time to do this. Euler's theorem says the following. If the GCD of n and k is equal to 1, then k to the power, the Euler-Tauschig function evaluated in n, is actually congruent to 1 modulo n. So this is what we're going to prove here. So why is this so interesting? Well, we will talk about an application which is a direct consequence of this theorem, which we'll call Fermat's little theorem. And that, in turn, we will use to explain the RSA algorithm and show how decryption works, and so on. So how can we prove this? We will start with a first lemma. And then we're going to do a few tricks, mathematical tricks, you will see it. So the first lemma is that if I know that the GCD, which is what we assume in the statement of the theorem, if I know that the GCD of n and k equals 1, then I know that A times K, if A times K is congruent to B times K modulo n, then this implies that A is congruent to B modulo n. Well, this seems to be kind of a straightforward lemma. I will only talk about its proof. So how do we do it? Well, first of all, I know that the GCD of n and k equals 1. So that means that I can create a multiplicative inverse, because I know that there is such a linear combination that, that will end up to 1. So I have the multiplicative inverse. I multiply both sides with this, and then I will end up to A is congruent to B modulo n. And actually, you can use some of the facts on your sheet to prove this. And in the problem set, you probably have seen that there are a number of problems related to this. And you will also, so you will recognize this and prove a few of these things yourself. Okay, so so this is, so let me see. So let me see what we have done here. Actually, I noticed that I've missed one statement that I would like to explicitly mention. I mean, I've used it a few times. Let me do that first, which is that we know that if the GCD of n and k equals 1, then this is if and only if the case if k has a multiplicative inverse. I've not yet explicitly stated this. And we can easily see this. Let me just give a quick proof to show how this works. Well, if the GCD is equal to 1, then we use the statement up there. So this is if and only if there exists a linear combination, so an S and a T, such that n times S plus k times T equals 1. Well, then I also know that there exists a T such that actually the difference between 1 and k times T is divisible by n. So n divides the difference of k times T minus 1. So why is that? Well, if I look at the difference between k times T and 1, that difference is n times S. And n times S is divisible by n. So now by the definition of congruence, I just apply the definition over here. We have written it out here. We can say that k times T is congruent to 1 modulo n. And this is the definition of the multiplicative inverse. So we have essentially shown that if the greatest common divisor between n and k is equal to 1, then it has a multiplicative inverse. Okay, we have been using this property over here because we assume that the greatest common divisor is equal to 1. So we now know that there exists a multiplicative inverse of k. We use that one to multiply away, essentially, the k out of this equation and get A is congruent to B modulo n. Also notice that we use that property over here. We said that we wanted to compute, what was it again? Over here. We started off with the GCD of m and p to be equal to 1, and I know p. And now I can compute the multiplicative inverse of m, and I should have said why it exists. And it exists because of that lemma that I just mentioned up here. Okay, so now let's go back to Euler's theorem. This first lemma we are going to use to prove a second lemma, and that second lemma we can finally use to prove the theorem. All right. So this lemma I will put on a separate board because it contains quite a number of steps to prove. So the lemma states that if we suppose that the GCD of n and k equals 1, so it's the same assumption as before, if we let k1 all the way up to kr to be those integers in the range 1, 2, 3, and so on to n minus 1 that are relatively prime. So these denote the integers relatively prime to n. Then we can prove a very interesting property. Now notice, by the way, that r in here is equal to the value of the Euler-Stochant function evaluated in n, because this counts the total number of numbers that are relatively prime with respect to n. So now we can prove something really spectacular. We can show that the set that contains all these remainders, the remainder of k1 times k, after dividing out as many multiples of n as possible, all the way to the remainder of kr times k, after dividing out as many multiples of n as possible, this set is actually equal to the set k1 up to kr. So this is what we're going to prove. And we'll do it in two steps. We first show that this set has exactly r numbers, so the cardinality of that set is equal to r, so that will be our first step in the proof. And over here we will show that every remainder is actually relatively prime to n, so it must be part of this set. So we will show that this is a subset of this set in the second part of the proof. And combining those two, we are able to prove equality. Why is that? Well, I have r distinct elements in this set. I have r distinct elements in this set. This one is a subset of this, so that can only happen if they are equal. So this is the method for the proof. Oh, I should. So we will start with the first part. And the way to do that is to see whether it is possible that that any of those any two remainders in that set, can they be equal to one another? We will show that that's not possible. So if it's not possible, then all these remainders must be different, and we have exactly r of those. So let's do this. So the proof for 1 is as follows. Let's assume that we have two remainders, say ki times k, and a remainder kj times k after dividing out as many multiples of n. Suppose that they are equal to one another. We are going to show that this can only happen if ki is equal to kj. And if you can see that, well, then we know that all these different remainders are actually different from one another. And if they're all different from one another, then we must have exactly r, because we have k1 up to kr in here. Okay, let's see whether we can do this. Well, if we know that these two remainders are equal to one another, we can look at them with respect to these definitions over here, and we can show that ki times k is actually congruent to kj times k modulo n. So why is this? Well, these two remainders are the same, and ki times k is equal to this remainder plus a multiple of n. This kj times k is equal to this remainder plus a multiple of n. So the difference between those two is also a multiple of n. And that's the definition of congruence. So now we can use our first lemma, which is stated over here. We know that we assumed in Euler's theorem that the GCD of n and k is equal to 1. If a times k is congruent to b times k modulo n, then we know that a is congruent to b modulo n. So let's apply it over here and take for a ki, and for b we can take kj. So now we see that ki is congruent to kj modulo n. And from this we will conclude, and that takes an extra step, that ki is actually equal to kj. So how can we do this? Well, we know that ki and kj are both in the range from 1 all the way up to n minus 1. So if I look at the difference between those two, so by definition of congruence, I know that n divides ki minus kj. I know that this one is in the range from 0 up to n minus 1. This one is in the range of 0 up to n minus 1. The only way how a difference of two numbers in this range can be divisible by n if this thing is equal to 0. And that means that ki equals kj. So now we are done with the first part, because we have shown that if I take any two remainders over here, it must be that they can only be equal to one another if actually the ki is equal to the kj. So we're looking at the same remainder. So the remainders in this set are all different, and there are exactly r of those. So now we go to the second part of the proof. And notice that so far we've only been proving the second lemma, and we still need to go to Euler's theorem as well. So it still takes a few steps. So how do we do the second part? Well, we saw in last lecture that we were explaining Euclid's algorithm, and we used essentially this property. We said that the greatest common divisor between n and the remainder of, say, ki times k and n is actually equal to the greatest common divisor of n and ki times k. So why is this again? Well, the remainder is actually equal to ki times k minus a multiple of n, right? So the greatest common divisor is therefore, between n and this, is the same as the greatest common divisor between n and ki times k. So you should have a look at last lecture. And now we are pretty much done. Why is this? Because we have assumed that the greatest common divisor between n and k is equal to 1. And ki, in the statement of the lemma, is relatively prime to n. And that means, according to the definition over there, that the greatest common divisor between ki and n is also equal to 1. So we know that both these greatest common divisors are equal to 1. So that means that there is no common divisor between n and this, except for 1, of course. So what does this say? Well, this means that this remainder according to our definition, is relatively prime to n, because this greatest common divisor is equal to 1. So if it is a integer relatively prime to n, then it must be one of those ki's, kj's in this set that is stated in the lemma. So this shows that it must be part of this set over here. So we have proven the fact that the set of all the remainders is a subset of the set k1 up to kr. So now we're done. So now that we have shown this particular lemma, we can continue and prove Euler's theorem. And I will probably need to wipe out some of this. Yep. So let's use this lemma to prove this theorem. So this is really a neat trick. So the proof of Euler's theorem is as follows. We are going to take the product of all those ki's over there and see whether we can find a nice relationship. So we take k1 times k2 all the way times kr. And we know, because those two sets are actually the same, that this is equal to the remainder, the first remainder, k times k1 times k, after dividing out as many multiples of n. And we go all the way up to the final one, the remainder of kr times k, dividing out as many multiples of n. So now we can see that, well, we have already shown that each of those remainders, right, is congruent to, in this case, this one is congruent to k1 times k modulo n, and this one is congruent to kr times k modulo n. So let's write this out. So it's k1 times k, and then we have k2 times k, and finally we have kr times k modulo n. So let's regroup those. We see k1, k2, all the way up to kr reappearing. And we have a k here, and we have that r times. So we have times k to the power r modulo n. So now we are able to again use this particular lemma over here. So what do? Well, we know that k1 is relatively prime to n, and k2 is as well, all the way up to kr. So this whole product is also relatively prime with respect to n. That means that the greatest common divisor of this whole product with n is equal to 1. So that means that I can divide out this whole product. Right? We have, so let's do this. We have, say, 1 times this product. We take this for A, and we take this for B. And then we can divide this whole thing out according to this particular lemma by using the multiplicative inverse of that product. So now we see that 1 is equal to k to the power r modulo n. And remember, in our theorem, r over here in this lemma, r is actually equal to the Euler-Totient function in n. So now this equation proves the whole theorem. Okay. So now I'm going to talk about RSA, which is the last part here. So maybe you all would like to have a little break of a couple of minutes, just to relax a bit, and then and shake hands with your neighbors and jump up in the air if you like to. All right, let's start with the RSA algorithm. So we have done everything up to this point, and we're actually, we have done these two over here. We still have to talk about Fermat's little theorem. But then we can go for RSA, and that uses this consequence of Euler's theorem. So Fermat's little theorem is actually talking about what happens if n is a prime number. It says, well, suppose p is a prime, then, and if we have k in the range 1, 2, all the way up to p minus 1, then we can conclude that k to the power p minus 1 is congruent to 1 modulo n. And we can directly prove this by using Euler's theorem. So how do we do this? Well, we know that p is prime, so the numbers 1, 2, all the way up to p minus 1 are actually relatively prime to p. So why is that? Well, p is prime, right? So the greatest common divisor between any of those with p is equal to 1. That's the definition of relatively prime. And we know that we can now apply Euler's theorem over here and see that k to the power phi of p is of course congruent to 1 modulo p. That's Euler's theorem. But now, since we know that these are the exact ones that are relatively prime, we can explicitly compute the Euler-Totient function of p, because there are p minus 1 numbers that are relatively prime to p. So that's the definition over here. So the number of integers in the range 1 up to p minus 1, they're all relatively prime. So we know that phi of p is equal to p minus 1. So now we have shown that k to the power p minus 1 is congruent to 1 modulo k. Now this is kind of interesting because we can use this theorem also to compute the multiplicative inverse of k in this particular case. So how do we do this? We just take k and we look at what happens if you multiply k with k to the power p minus 2. Well, this is equal to k to the power p minus 1, which is congruent to 1 modulo p, according to our Fermat's theorem. So now when we look at the definition of multiplicative inverse over here, we see that k to the power p minus 2 is actually the multiplicative inverse of k. So k inverse is actually equal to k to the power p minus 2 modulo k. All right, so this theorem we're going to use now in the description of RSA. As I said, it was only decades later, after Turing, Rivest, Shamir, and Edelman were the first to really show how number theory could be applied so successfully in cryptography. And they essentially showed the first public key encryption scheme in which a sender and a receiver do not necessarily have to exchange a secret key. That's not necessary. So they had a public key method. And that's still used today. And it's a great invention. So how does RSA work? Again, we have to talk within an encryption scheme about what happens beforehand. So beforehand, we need to generate this public key and a secret key. So the idea is that the receiver creates a public key and also a secret key. He will publish the public key and he will keep the secret key for himself. And now anybody can use the public key to encrypt a message. The encrypted message is sent to the receiver and he is going to use his secret key to get back to the plain message. So how is he going to do this? Well, in the first step, the idea is to generate two distinct primes. Turns out that this can be done in a very efficient way. There are lots of primes among the integers, so you just sample, and it turns out that you can test primality with a pretty high probability very efficiently. And recently, actually, there has been a deterministic algorithm that is polynomial in a number of bits of the primes that can actually tell you whether you have a prime or not. So you can do this. 2, we are going to create a product of these two distinct primes, and that's where our assumption is going to help us, that it is hard to factor a product of two large primes. That's going to be the underlying hardness assumption of the RSA encryption scheme. So let n be this. 3. We're going to select an integer e such that the greatest common divisor of e with the product p minus 1 times q minus 1 is actually equal to 1. And the public, and once we have created this, the public key is going to be a pair. So is the pair that consists of e itself together with n. So that's the public key. And the secret key is going to be computed as follows. In step 4, we are going to compute d such that d times e is congruent to 1 modulo that product of p minus 1 times q minus 1. Can we do this? Yeah, because the greatest common divisor between e and that product is equal to 1. And we have shown over here that therefore it has a multiplicative inverse. So first of all, we know that the solution d exists, and we can also efficiently compute it. So the secret key is going to be the pair that consists of d and also n. So how does it work? The sender knows the public key, e and n, and uses those to encrypt the message. I will explain it in a moment. And then the receiver knows the secret key, d and n, and then is able to decrypt it. Okay, so let's see how encryption works. And then we will have to do a lot of mathematics to get the decryption going. So m prime, which is computed, so the encrypted plain text is computed as the remainder of m to the power e, which is part of the public key, and then dividing out as many multiples of n as possible. It turns out, and we're going to prove this, that decryption works as follows. We can compute m by using m prime, so we receive m prime. What do? We're going to take m prime, raise it to the power d, which is part of the secret key, and then dividing out as many multiples of n. Now, why would that work? Why would this work? So let's prove this step over here. Well, it turns out that we can apply Fermat's theorem, and the idea is as follows. So let's have a look. We know that m prime is equal to the remainder of m raised to the power e, which is congruent to m to the power e modulo n. We have seen this now a number of times, right? So what does this imply? This implies that m prime to the power d is actually is congruent to m to the power e to the power d. So I just raise this side to the power d, and I raise this side to the power d, and I still, and I know now that m prime to the power d is equal to m to the power ed, congruent to m to the power ed modulo n. So now we know that there exists an integer r. We are going to use the fact that we have that e and p minus 1 times q minus 1 have a greatest common divisor of 1. So we know that e times d is actually equal to 1 plus r times p minus 1 times q minus 1. Actually, what I used here is the fact is this over here. By the definition of congruency, I know that the difference between those two, d times e and 1, is divisible by this product. So I know that there exists an integer such that e times d equals 1 plus a multiple of that product. That's how it works. So we know that m prime to the power d, we already saw that it is equal to m to the power ed, which is congruent to, well, we just replace ed by 1 plus r times this multiple. So we have m to the power 1 times m to the power, this part, r, p minus 1, q minus 1. Okay. So now we're finally going to get to Fermat's theorem. We know that n is the product of p and q. And I'm not actually sure why I do this here, but okay, so let's apply Fermat's theorem and see how we can use this. So if m is not congruent to 0 modulo p, well, then we can apply Fermat's theorem. Where is it? It's over here. We can only apply this if k is in the range from 1 to p minus 1 is not equal to 0. So if m is not equal to 0, not congruent to 0 modulo p, then we can apply the theorem and state that m to the power p minus 1 is congruent to 1 modulo p. And in the same way, we can do this for q. So if this is not true, modulo q, then m to the power q minus 1 is congruent to 1 modulo q. So here we have used Fermat's theorem twice. Now we can apply what we have learned before, which is what we wrote down over here. M prime to the power d is congruent to this modulo n. Now n is p times q, so let's have a look what that means. It means that since n is a product of p and q, we can also look at this congruent modulo p. So in particular, we know that m prime to the power d is congruent to m times m r p minus 1 times q minus 1 modulo p. Why is that? Well, we know that n divides this difference by the definition of congruency. N is equal to p times q. So if n is dividing this difference, also p is dividing this difference. So that's why we can write that m prime to the power d is congruent to this thing, modulo p. And of course, we can repeat this for q. So let me write this out as well. So there it is. So now we can use what we have figured out over here. So we know that if m is not equal to 0, then this thing over here cancels out because m to the power p minus 1 is congruent to 1. So we have that m prime to the power d is congruent to m modulo P if m is not congruent to 0 modulo P, right? Because if m is not congruent to 0, we have this particular equation, we plug it in over here, this all cancels, and we just are left with m. Now, if m is congruent to 0 modulo P, well, then we can see that it is equal to 0, so it's equal to 0. So this actually holds for any case. Now we can do the same for Q, the same argument, and show that this must hold. So now we know that P divides the difference of m prime d minus m. Q is another prime that divides this difference. And the only way that that is possible is if the product of P and Q is dividing both, is dividing this particular number, this difference. And we have two different primes that dividing the same number, so the product must divide it. So P times Q divides m prime d minus m. Oh, but P times Q is equal to n. So now we're almost done, because now we can state, by the definition of congruency, that m prime to the power d is congruent to m modulo n. Now, since m is a message that is in the range so I did not write it down here, so m is a message which is in the range of 0 all the way up to n minus 1, we know, and we have seen that before with Turing's code, that we can rewrite this and say that m equals the remainder of m prime to the power d after multiplying out as many multiples of n as possible. So here you go. So this is the decryption rule, and it works. We have shown that this equation truly holds. So RSA has really withstood the test of time. It's already out there for many decades, and it's still widely used. I wanted to talk a little bit about this, but there seemed not to be enough time. But I'd just like to mention that, only in 2009, Greg Gentry proved a beautiful theorem and was able to evaluate Boolean circuits or say, a certain type of programs under encryption. So you can sort of add and multiply ciphertext encryptions together, and it is as if you multiply them at the plaintext level. That was a fantastic, that was an enormous open problem, and he solved it. And only a few months earlier, in 2010, in joint work with Greg and some other colleagues at IBM, we showed that with very simple arithmetic that just uses modulo P and modulo 2 kind of things, we could show a construction that uses that has such a property, such an encryption scheme over the integers. So there's still a lot of stuff going on in this area, and really we use this type of very basic stuff. The problem in cryptography is to show that it is secure. So we have to show that breaking the scheme needs to be reduced to some really hard problem, and that is usually, and that's always the really difficult part of such type of research. Okay, well, have lots of fun with the recitation.
Wonder how much I wrote down, you never broke down. My back used to be up against walls, it's on the ropes now. Fighting for that feeling we had in your Laredo. Back when you saw the thorns on my crown, more like a halo. My conscience punished me for the past while I was out there trying to ball. Bet you seen through the mask, hope I ain't being brash. If I say you could've split it with me, girl, you would see riches with me if you stuck around through the rags. My motivation these days is different. I mostly beat on myself, I don't wanna spoil a couple things I prayed for and was gifted. Just peep the drive, see how I stayed in my lane when they shifted. I knew that time could not erase what my destiny's written. Right there next to these writtens. In my skin and my DNA like the one that was risen. I'm out that grave and I'm where life is the only decision. I'm not alone in my plight, I want you alone for the flight. About to take off in a minute.
I dreamed it up, changed out my lifestyle. New money, nice house, I cleaned it up. And that seems enough, but one thing really on me, I'm thinking of. In my sleep I see new scenes of a just you, me, two rings, no strings to cut. But I don't know what you want. Do thinking of it make me wrong. It hasn't been too long.
Yeah, still I got my eyes on the prize that never else in sight, just tunnel vision. If I got commas missing, I don't know who might come up missing. I don't know who gon' beat her through it. Thought you were at one time, that got proven not to be so true. I got left halfway out my mind, had to gather some things, rearranging what really matter, kill casual flings. Set the goal and saw nothing after, had to take a risk. Bet on me, cause that's where the well. Before you fantasize of them, you should dream of a better self, and that's for real.
I dreamed it up, changed out my lifestyle. New money, nice house, I cleaned it up. And that seems enough, but one thing really on me, I'm thinking of. In my sleep, I see new scenes of a Jesuit, 2 rings, no strings to cut. But I don't know what you want. Do thinking of it make me wrong? And has it been too long?
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's get started. I once taught with a professor who was lamenting the fact that as the term progresses, attendance at lecture tends to drop off and gets pretty dramatic by the end of the term when you're lecturing and nobody's there. And I asked him what he did about it. And he thought about it and he said, there's only 2 things that can get students to come to lecture: candy and sex. Now, we've already tried candy. So today we're going to talk about sex. In fact, we're going to use graph theory to address a decades-old debate concerning the relative promiscuity of men versus women. Now, graphs are incredibly useful structures in computer science, and we're going to be studying them for the next 5 or 6 lectures. They come up in all sorts of applications: scheduling, optimization, communications, the design and analysis of algorithms. In fact, next week you're going to see how 2 Stanford graduate students became gazillionaires because they used graph theory in a clever way. But let's talk about sex. The issue that we're going to address today is one of the most talked about and most well-studied questions in all of human sociology. On average, who has more opposite gender partners, men or women? Now, opposite gender is going to be important. And by this I mean 1 boy and 1 girl. All right, I'm not making a political statement. It's just that the math is a lot easier that way, as you'll see. Now, I'd like to start by taking a poll here to see what you think about that. So raise your hand if you think men, on average, have more opposite gender partners than women do. Ooh, only a few. You can. Yeah, 1 on 1. Okay, so let's say over the course of their lives, or over the course of 2010, that men in America have more opposite gender partners than women in America, say in 2010. Raise your hand if you think men have more going on. All right, a bunch of you. Raise your hand if you think women have more opposite gender partners. Oh, this is unusual. Maybe even more voted for women, but it's close. Raise your hand if you think it's equal. All right, about the same. Raise your hand if you think there's no way to know, that it's hopeless to really figure it out. All right, nobody goes for that. Yeah, all right, good. All right, well, now in the popular literature, I think the feelings are different than expressed here. Pretty much universally in the literature, it's believed that men have more opposite gender partners than women. And in fact, you can even think about that if you think about literature. You know, the leader of the harem is always a man, and he's got lots of women. You know, in polygamous cultures, it's always the man that has multiple wives, not the reverse. Now, not surprisingly, this issue has been studied scientifically, I'll put in quotes, extensively. In one of the largest studies ever done, researchers from the University of Chicago interviewed 2,500 people at random over several years. They brought them in on many occasions to try to get the answer for the question once and for all. And they wrote this 700-page book called The Social Organization of Sexuality, Sexual Practices in the U.S. Actually, walking around with this book has proved to be a little embarrassing. Last week, my 11-year-old daughter saw it, and she goes, "Dad, why do you have this sex book?" And I grabbed it back and I said, "That's for the course I'm teaching." I thought I'd gotten away with it, and everything was fine. And then later that day, she texted all of her friends about the new news that, what do you know, her dad teaches sex ed at MIT. Anyway, this study concludes that on average, men have 74% more opposite gender partners than women. It's one of their central claims. And this is in the US. Okay, now, when you think about it, that sounds maybe reasonable. You know, it might be okay. But not according to ABC News. They did a poll of 1,500 people in the country in 2004 and concluded that the average disparity is much greater. In particular, in this study, they said that the average man has 20 partners, I'm assuming over their lifetime, and the average woman has 6. And this gives a disparity of 233%. So ABC News did a smaller survey, says that it's 233% here. Much more than 74%. Now, ABC News claimed this is one of the most scientific studies ever done, and that there was a 2.5% margin of error. Now, we'll actually talk about what that means mathematically later in the term when we do probability and do study polling. Now, of course, I should also mention that ABC News is the one that said Al Gore won the presidential election in 2000, I mean. Now, the study is called American Sex Survey, A Peek Between the Sheets. That doesn't sound so scientific. And it was on TV, on Primetime Live in 2004. The promo for this is really good. It says, a groundbreaking ABC News Primetime Live survey finds a range of eye-popping sexual activities, fantasies, and attitudes in this country, confirming some conventional wisdom, exploding some myths, and venturing where few scientific surveys have gone before. By the end of today, we're going to agree with that last statement. Okay. Now, who do you think's right? University of Chicago? Who votes for 74% as being pretty close? A few of you? I've already sort of slammed these guys. Who votes for ABC News as being more accurate? Yeah, nobody. Who votes for No Way to Tell? I got some votes there. All right. So how do you tackle this problem? You know, in theory, we could do our own 6042 survey. I don't know how much we'd really learn, and for sure I'd get fired. So I don't think we're going to do that. But fortunately, this is the kind of question that can be handled and actually answered by graph theory. Even though it might be more interesting to interview thousands of people and find out what's going on, that's not as efficient as using graphs. So let me start by defining what a graph is. Informally, a graph is just a bunch of dots and lines connecting the dots. It's actually very simple. So here's a graph. These are the nodes, and they're connected with these lines that are called edges. And often the nodes and sometimes the edges are labeled. For example, we might call this x1, x2, x3, x4, x5, x6, and x7. All right, that's an example of a graph. Now, this being a math class, we've got to give a formal definition of a graph. And we'll usually use the formal definition. A graph G is a pair of sets, often called V and E, where V is a set of elements called vertices or nodes, and it has to be non-empty here in this class. And we'll go back and forth between vertices and nodes. Even in the text, we use both words interchangeably. And E is a set of two-item subsets of V, and they're called edges. So for example, over here in this picture, V is the set of nodes is x1, x2, x3, up to x7. That's the nodes. And E, the set of edges, is pairs, unordered pairs of vertices. So for example, x1, x2 is an edge. And it's the same as the set x2, x1. Doesn't matter the order here. Later, in a week or so, we'll talk about directed graphs where the order matters. x1, x3 is also an edge here. And so on. I think we've got, let's see, 1, 2, 3, 4, 5, 6, 7 edges in this graph. And the last one would be x5, x7. Edges are also sometimes written with this notation. x1 line, x2 is another notation. And then later, when you talk about directed edges, we'll put a little arrowhead on one end of this. Now, the definition of a graph is really pretty simple. Just think of it as dots and lines if you want. But there's often differences in how people define graphs. For example, in this class, we don't allow the empty graph, i.e. the graph with no nodes. So we're going to insist that every graph has to have at least one node in it. And that's just to make the theorems we're going to prove be true. Otherwise, there are some theorems that are false for the special case of the empty graph. But we don't require the graph to have any edges. In fact, it's possible you have a graph with nodes but no edges. For example, this graph, 3-node graph. So here G equals VE, V equals x1, x2, x3, and E is just the empty set. Now for a general graph, when you do have edges, we say that two nodes, call them xi and xj, are adjacent if they're connected by an edge, namely if xi, xj is an edge. All right, so for example, x5 is adjacent to x7, but it's not adjacent to x4. There's no edge there. Closely related is the definition of incidence. An edge E, which is xi, xj, is said to be incident to its endpoints, xi and xj. Okay, so for example, if I label that as edge as E, E is the edge x1, x2, and it's incident to x1 and incident to x2. then we can talk about the degree of a node. The number of edges incident to a node is called the degree of the node. So for example, what's the degree of x5 over here? 3. So in this case, the degree of x5 equals 3. The degree of x7 is 1. These guys all have degree 0. There's no edges incident to them. Now, in this class, we're going to look at only simple graphs, at least for a while. A graph is simple if it has no loops or multiple edges. Now, a loop is an edge that only connects up one node. That's a loop, and we don't allow it. A multiple edge is where you've got two edges that are really the same, that connect the same endpoints. Also called a multi-edge. And those we're not going to have in simple graphs. We don't allow this. We don't allow that. Any questions so far about what a graph is? OK. So, all right, how are we going to use a graph to model the problem of opposite gender partners? That's the question we're after. So, any thoughts about what the nodes of the graph are going to represent? What is it? People. Yeah, so we're going to have people. And in fact, there's two kinds of people here. There's men and women. All right, and we got nodes here for the men. And in fact, in America, there's a lot of nodes here. All right, and so this might be, oh, I don't know, say that's Tom Cruise and Nicole Kidman. Now, what's the edge going to represent? Partners. All right, they were opposite gender partners. And there's actually more edges probably here. You know, we could have Penelope here and Katie here. And, well, probably lots more. I probably don't even know them all. And Ben's over here with Nicole. And Nicole got Jude and Keith. There's actually a website you can go to get a lot of these things here. And Katie went with Josh. It's called whosdatedwho.com. And you get a big graph. You can start filling in the edges. I don't know how reliable it is. Now, it's really critical that we're only looking at edges from here to here. All right, so if there's an edge between Tom and Ben, I don't want to know about it. All right, so just opposite gender partners. OK, now in the USA, the number of nodes here is about 300 million. All right, about 300 million people. And the number of men nodes, male nodes, call these VM, and this is VW. By the way, I'm using cardinality notation. When I put bars around a set, that is denoting how many are in the set. In the US, there's about 147.6 men out of the 300. And the number of women, got a W here, is about 152.4 million. So there's a little bit more nodes on this side of the graph than that side in the US. What about the edges? Any idea of how many edges there are here? We don't know. I sure as heck don't know, how many edges there are. So that we don't know. The cardinality of the edge set we don't know. And we're not likely to figure out. I don't even think these surveys really can estimate that. But what we are trying to figure out is the ratio of the average degree of the men to the average degree of the women. Because the number of opposite gender partners you have is your degree here, and you're looking for the average guy degree compared to the average female degree here. That's what we're after. All right, so let's define that quantity. Let's let A sub m equal the average number of opposite gender partners for men. And we can let AW be the same thing for women. All right, now we're trying to figure out, to answer this question, what is AM, the average guy degree, over the average woman degree? And in particular, the University of Chicago says, they say it's 1.74, that the average guy has 74% more opposite gender partners than the average woman. ABC News says it's 3.33, that it's 233% more for the men than the women. Now we're going to figure this out, what this ratio is. All right, just use a little bit of math here and a little bit of graph theory. So let's write a formula for AM. Well, we're trying to figure out the average degree over here. Well, that's pretty simple. We just add up all the degrees and divide by the number of nodes. And that'll give us the average degree. So the average degree is the sum of the degrees over all men, x in the set of men, of the degree of x, divided by the number of men. All right, can somebody give me a simpler expression for this? It doesn't have that nasty sum in it. E, cardinality of E. I'm adding all the degrees here. Well, that's just another way of counting all the edges. Because every edge shows up once and only once in a degree count here. And this is where we use the fact we have opposite gender partners. Right? Because if I had some edges over here, they wouldn't get counted in the sum of the degrees here. All right? So this is just the cardinality of the number of edges divided by the number of men. Any questions about that? Because this is an important statement about graphs in general. When I have a graph like this, which is called a bipartite graph, we'll talk about more a little bit, but where the edges go from the left to the right, if I sum the degrees on the left, I'm just counting the number of edges. All right. Let's figure out a formula for the average number of partners for the women. Well, that's simple. That's just sum x over the women, the degree of x, divided by the number of women. Let me rewrite that so it's clearer. What's a simpler expression for this? Yeah, this sum, adding the degrees of the women, is just the number of edges, right? So that is cardinality of edges divided by the number of women. All right. Well, now we can solve for our formula, average over men over average of the women. That's E over Vm divided by E over VW. Wow, this is nice. I don't know what the number of edges is, but it just canceled out. And this is just the number of women divided by the number of men. And in fact, we know that that's this number divided by that number, which is about 1.0325. So we just proved that on average, a man has 3% or 3.25% more opposite gender partners than women. No need to do the interviews or spend years doing it. That is the answer. And it has nothing to do with the promiscuity of men or women. Nothing at all. All right? So the Chicago study is way off, and the ABC News study is completely nuts. It just can't be right. This is a proof. All right, now, what happened here? Well, what's going on? What's the reason for why this is true? Yeah?
Well, if a male has a female partner, then a female has a male partner.
Yeah.
And you're not looking at like how many males are going to one female. Like the promiscuity isn't even like a part of the question.
That's right. You're just, it takes two to tango, right? Every time you got a guy, you got a woman, and you have the number of relationships going. The average for the men is that number divided by the men. Average for the women is that same number divided by the women. And so if there's more women, they're going to have less partners on average. Has to be. So it really was a stupid question. It's very, very simple to answer. Now, as it turns out, there are endless studies like this in the literature. In fact, a few years ago, the Boston Globe ran an explosive story about the study habits of students on Boston area campuses. And their survey showed that, on average, minority students tended to study with non-minority students more than the other way around. All right? And they went on great length consulting the experts as to why this might be true. Why is it that minority students study with non-minority students more than the other way around? Now, can anyone tell me why it is certainly true and not surprising why that's the case? Because they're a minority. There's fewer minorities than non-minorities. End of story. We don't need the sociology PhD from down the street to explain it to us. All right. We're going to see a lot of other bogus studies later. This is not unusual, especially when we get to probability. Just every day there's a new one in probability. Any questions about this before we leave? Unfortunately, that's most all we'll say about sex today. Okay. Now, in this example, we used an edge in the graph to denote some kind of affinity, between two nodes. The two nodes liked each other in some sense if they were connected by an edge, or they had a relationship of some kind. There's lots of examples in computer science where you use an edge to denote just the opposite, that the two nodes can't be near each other or don't like each other. For example, consider the problem of scheduling final exams at MIT. And they do this after they find out all of your schedules. And they try to schedule the exams so that you don't have to take two at once, or there's as little of that as possible. For example, let's do an example here. Say we look at these 5 classes. Take 6041. And this may not be totally accurate, but roughly. So I've got 5 MIT classes, and I'm going to put an edge between pairs of classes that have overlapping student enrollment. So in this case, for example, we've assumed in drawing this graph that you can't have our exam the same time as 6002. on the assumption there's students in both classes. But you could have our exam the same time as 6034 because there's not an overlapping student or student in both classes. So the exams could be scheduled at the same time. So we've used a graph to represent which courses can't have their exam at the same time. Now let's also suppose we have a set of slots for the exam. And say they're all on a Wednesday. And the first slot is Wednesday from 5 to 7. And the next one is 7 to 9. And then the next one is 9 to 11. And then 11 to 1 in the morning. And then 1 to 3. Getting pretty late. And your job is to figure out how not to have to use these later exam slots. You'd like to use as few as possible so you're not, going too late at night or come before the holidays so you're not having exams on Christmas and New Year's, for example. So the goal is to assign slots to the nodes. Put every node in a slot so you don't have nodes hooked by an edge getting the same slot. Now, this is an example of what's called a graph coloring problem. So let's define that. Given a graph G and K colors, assign a color to each node so that adjacent nodes get different colors. All right, and then the minimum number of colors you need is called the chromatic number of the graph. So the minimum value of K for which such a coloring exists is the chromatic number of the graph. And it's denoted by the symbol chi of G. All right? Because usually you want to use a small number of colors. Now, what does a color represent when we're dealing with this problem? What's the meaning of a color? A time slot. Okay? So let's call this time slot C1, C2, C3, C4, C5. So there's 5 possible colors. Now, of course, we could color this graph with 5 colors. Every node could just get its own color. But then somebody's taken their exam, from 1 to 3 a.m., and, that's a bit of a pain. Let's see if we can do less than 5. Let's say I give this color 1. And let's give this one color 1. That's OK, because they're not connected. I can't give this one color 1, so I give it color 2, say. Now this one I can't give color 1 because this guy got it. He can't get color 2 because that guy got it, so I give it color 3. And, well, I can't do 1, 2, or 3 here, so I got to go to color 4. All right, so 6042 will get the 11 p.m. to 1 a.m. slot. Not so good. Can we do any better? Can we get away with 3 colors? Some say yes, some say no. How many people think you can do 3 colors on this graph? A bunch. How many think you can't do any better? All right, the vote is mostly for 3. Well, let's see. Any ideas? Anybody see how to do 3? Yeah?
Sine C4 to 6034.
Sine C4 to 6034.
Or C1 to 6042.
C, I can't do C1 to 6042. It crashes, but can I do, yeah?
Put C1 and 6003.
C1 and 6003.
And get rid of C1 and 6034.
Get rid of, make this a C2. Oh, yeah. All right, these got C1, they're not adjacent. These got C2, they're not adjacent. This can now get C3. So we can have our exam from 9 to 11, which is better. All right, can anybody do it in 2 colors? All right. Can anybody offer a reason why 2 colors may not be possible? Yeah?
Because let's say you could do it with 2 colors.
Yep.
6041 and 6002 have to be different colors.
Yes.
Say C1 and C. 6042 can't be C1 and it can't be C2.
Yeah. Good. So you can't do 2 colors because these 3 guys would violate that. You got a triangle here. Each one of these guys has to be different than the other 2. So 2 colors can't work. You got to have at least 3 in this case. So 3 is optimal. We have just shown that for this graph, the chromatic number is 3. All right. Now, in general, doing what we just did is very hard. No one knows a fast algorithm for determining the chromatic number. In fact, it's a weird kind of problem because it's easy enough to check that a coloring is okay. If somebody put a coloring on the board, you can check, oh, that works really simply. You just check every edge and make sure the colors are different. But figuring it out, as best we know, you got to try an exponential number of possibilities. So if I had 100 nodes here, my running time of the algorithm to check all the possibilities would be exponential in 100. Yeah?
The highest degree of each node or nodes?
No, but it's no worse than something like that, as we'll see in a few minutes. That's a great observation, and we're going to come back to that in a few minutes. But it's not just that. Okay? Now, in fact, even figuring out for an arbitrary graph if 3 colors can be done, called the 3 coloring problem, that's really hard. No one knows how to solve that in less than exponential time. In fact, it's called one of these NP-complete problems is what it's called. How many people here don't know about NP-completeness? Is everybody? All right, so a lot of you haven't seen NP-completeness. Okay, so there is a class of thousands of problems. In fact, there's books that list these 1,000 problems that are all NP-complete. Somebody's proved they belong in the class. And what that means is that if somebody gave you a solution, like a coloring here, it's easy to check really quickly if it's valid. But figuring it out is really hard, and if you figured out how to solve one of those thousands of problems, like suddenly you figured out how to tell if any graph could work with 3 colors, you would solve automatically all other thousands in the book. So it's this book of problems you will constantly run into in your career in computer science. And it's bad when you run into one because there's no good algorithm to solve it known. But if you just solved one of them, the other thousands would suddenly be solvable quickly. Even better, you win $1 million prize, one of these Millennium Prizes we talked about in the first lecture. Even if you show you can't find a fast algorithm for one of them, that means that none of them have fast algorithms, and you also get $1 million. So this is the central problem in computer science, in theory of computing, is whether or not you can solve these NP-complete problems. Now, actually, lots of people have claimed to do it. And in fact, there was a lot of buzz in the community about a month ago when actually a reputable researcher at HB Labs said he'd done it. He'd proved that you can't solve NP-complete problems. And he got people going for probably at least a week until they discovered a fatal flaw. And the proof was actually bogus. So no one still knows if you can solve these NP-complete problems quickly. Now, the problem is, in practice, you run into these things all the time, like MIT really does have to schedule the exams. So you got to do something. You can't just go say, hey, it's NP-complete, so no exams this year, or whatever. That's not going to fly. You got to do something. So now, this is a problem. Many of you, when you go into careers, are going to be faced with this. You got to do something. Any thoughts about an algorithm for coloring graphs that might use a small number of colors? It doesn't have to always work, or you're going to win a lot of money if it does, but a simple algorithm, you can't take e to the 100 steps. You got to be linear, probably, or quadratic time. That could get you a small number of colors. Any thoughts about what you'd do? Yeah?
Number of degrees of the node.
The number, what about it?
Like the highest degree in that node for 6442 is degree 3.
Yeah?
So you can use that.
Good. All right, but what do I do with that info? So I found a node with high degree. There's three of them that have degree 3 here. What do I do with them?
Pick a different color.
Pick a different color. That means I've colored some of the others. If I pick a different color, do I start with them or do I finish with the high degree nodes? Because you got to assign the colors to them. And high degree is important to be thinking about. We're going to prove a theorem in just a minute about related to degree and coloring. Start with them and do what with it? Color it?
Yeah, and then assign the ones that aren't connected. If hopefully you can fit the same slots.
Okay, so I could, here's a degree 3 node. I could start with color 1 for that. And then what do I do next? I pick, its neighbors have to get different colors, I guess. You'd start coloring the neighbors.
Well, I guess I would, my first instinct would be to color all the ones with the most degrees first.
Okay. And what color would you use for them? Different ones if they're connected, or if they're not connected, you'd still use different ones?
Only if they're connected.
Only if they're connected, use different ones. And so if they're not connected, you use the same colors? Yeah? All right, so this is actually, you're getting close. It actually works pretty well. The underlying principle you're sort of thinking about here is you've got some notion of the order in which you're going to process your graph. And you're going to start with the high degree nodes in your case. And as you go along, you're going to start coloring the nodes. And you're going to make sure you color them legally. And it sounds like you're going to color them with a low color, all right, as you go along. And that is probably the most basic graph coloring approach. And you could almost say is a generic approach. So let's define that and then prove some facts about it. Most of the graph coloring algorithms in practice are based on this approach. And we're going to call it the basic graph coloring algorithm. And for a graph G with vertices V and edges E. So the first step is going to be to order the nodes from 1 to n. Now, in your case, you were suggesting an ordering where I have the high degree nodes first. All right? But for now, we're not going to specify that. We're going to make it any ordering you want. And then we're going to have a notion of an order on the colors as well. And I don't know how many colors, but they're going to be numbered 1, 2, and so forth. And then we're going to process the nodes one at a time. To n. we color the node. So at step I, we color the ith node v sub I with the lowest legal color. And by legal, I mean you don't color at the same node as another node that's already been colored that it's the same that it's adjacent to. All right, so let's try this. In fact, this is sort of the algorithm I used initially to color the exam graph over there. All right, so let's look at that. So let's say let me erase the colors here and put an ordering on the nodes. So let's say I ordered them with 6034 first. So this will be V1. Then 6041 is V2. Then V3, V4, V5. If that's my ordering, what color would I assign to 6034? 1, C1. I'd color it first to get C1. What color does 6041 get? C1 as well. It's the lowest possible color that's legal, and it's not hooked to this guy, so C1 is legal. What color do I give here? C2. Then I color this one next. Can't do C2, can't do C1, so I pick C3. And then I get the 6042 last, and I can't do 1, 2, or 3, so I do 4. All right, so this algorithm with that ordering gave 4 colors. However, we know there's a way to do a different ordering that gives us 3 colors. In particular, let's see if we do this. What happens if we use this other ordering? Erase these. Say that's V1, V2, V3, V4, V5. Now I get C1. This will be C2, C1. What's this one get? C2. Oh, much better. C3. So different orderings result in different numbers of colors here. So the whole art now becomes finding a clever ordering. And some people have already had good ideas. Pick the largest degree nodes first. And in fact, if you simulate the algorithm on lots of graphs, you do better on average when you color the large degree nodes first. And then if you start to use more exotic orderings, you can do even better if you take a lot of graphs that are out there and run your algorithm and see how well you do better with more sophisticated orderings. In fact, this was my senior thesis back when I was an undergraduate student, was trying to figure out better and better orderings that worked for graphs. And at the time, it caused a bit of a problem. I was an undergraduate at Princeton. And Princeton, to this day, I think, still has exams after the holidays, the Christmas holidays, New Year's holidays. And the students wanted to have the exams before Christmas because they hated going home for the holiday, and then you got to worry about your exams when you come back. And the faculty said, no, there's no way to get them all compressed into a small number of days. Now, I wasn't aware of all that at the time, but my thesis was go figure out good ordering. So I tried lots of different orderings, and I tried the largest degree first, and recursive versions of that actually work very well. And then tried it on the Princeton exam graph. And lo and behold, you could actually squish it down so you could give all the exams, I think it was 4.5 days. Plenty of time to give them before Christmas, which caused a fair scandal at the time because then the faculty had to come clean that they just didn't want to bother having the exams before Christmas. Now, this algorithm is an example of what's known as the greedy algorithm. Now, in a greedy algorithm, it's always simple. You just go one step after the next, taking the best you can do at each step. You never go back and try to make things better. You never do hill climbing. If you're familiar with that term, you just always keep it simple, one thing after the next, very fast. Sometimes works great in practice. Sometimes doesn't. But it's always where you'd start, some simple approach like this. Now, this algorithm actually, even if you don't try to monkey with the ordering, even for a worst case ordering of the nodes, actually does pretty good for a lot of graphs. And in fact, it does really well, as somebody already asked about, if all the nodes have low degree. So let's state that as a theorem, and then we're going to prove that. So if every node in a graph G has degree at most d, so that's the biggest degree in the graph, d, then this basic algorithm uses at most d plus 1 colors for G. No matter what the ordering is, you'll never do worse than d plus 1 colors. So what's the value of d for our exam graph over here? D is 3. Every node has degree at most 3. And so it says that no matter what ordering you picked here, you'd get at most 4 colors. Now you might do better. In fact, we found an ordering that got 3. So it's possible to do better. So let's prove this fact, because this makes a difference. Say you have a graph with hundreds of nodes, but every node has degree at most 3. Well, that says you only need 4 colors, even if the graph has 1,000 nodes. And that's very useful. So in that kind of situation, it does very well. So let's prove that. Any ideas as to what proof technique we're going to use? Invariant, close. Not quite an invariant, but close. What? You know, well-ordering principle, yeah, we're going to use the equivalent version of that. We're going to use induction. I'm not a, if you like it's equivalent to well-ordering. So if you like well-ordering, you can do it that way. I think it's easier using induction here. So the proof is by induction. All right, so the first thing we need is an induction hypothesis. Any thoughts about what the induction hypothesis should be? Yeah?
If you have a graph with n nodes, then where the degree of any node is less than or equal to d, then you can do it in at most d plus 1 colors.
That's great. You're going to do really well in the midterm, because you put an n into this thing. But there's not an n here to start. What are most people going to do? We used to ask this, actually. We asked this once on a test many years ago, and it was an utter disaster. Because what did everybody do? Maybe one student or two put an n into here. But what's the natural thing to do to induct on here when you look at this statement? You're going to induct on D, right? Because the first thing you do is you make this be your induction hypothesis. There's only one thing to use. So you're going to have your predicate be P of D, and it's going to be that. Now, it didn't occur to us that's what everybody was going to do. It should have. They all did that, and it was a disaster. Because if you do this, well, you've got to take a graph with maximum degree D, or D plus 1 in the inductive step, pull out all the nodes with degree D plus 1 to get a graph with now degree D. And that's a mess. You just pulled out a lot of nodes, potentially. Color that in D plus 1 colors. Now put all that junk back in and say you only used one more color? Nightmare. And these are MIT students under pressure. That was a nightmare. So that does not work. And in fact, we will ask an induction question on graphs on every test you take in this course. All right, it will happen. And so usually, with induction, you take this as your induction hypothesis. With graphs, you have to be careful. And the worst part about this is we tell people when this doesn't work, use a stronger induction hypothesis. So students tried to make it stronger, but they're still stuck on D, and it was still a disaster. With graphs, you do something different. And the first thing you do with a graph usually is put n in here. And if it doesn't work with n, the number of nodes, you put in e, the number of edges, and induct on that. And so what you said is exactly the right thing to do. Don't do this. or at least don't spend too much time on it, pretty quickly try this. If every n node graph, if every node in an n node graph G has degree at most d, then the basic algorithm uses at most d plus 1 colors. And now you induct on n. And almost always in graphs, that's the first thing to try, even if it's not in your theorem statement. Any questions about that? All right. Well, let's start with this and see if we can make this one work. So what's the next step in our proof? What do we got to do? Base case. And the base case will be not n equals 0, because we can't have a 0 node graph, but n equals 1. And how many edges do we have? 0. If there's one node, we don't allow loops, so it's 0 edges, which means that the degree of our graph has to be 0. There's no edges. And of course, there's only one node, so one color is going to work. And that happens to equal d plus 1. All right, so the base case is true. For one node graphs, you can always use d plus 1 colors, where d is the max degree. All right, next we have the inductive step. So here we assume Pn is true for the induction. And now we look at an n plus 1 node graph to show Pn plus 1 is true. So we let G be any n plus 1 node graph. We've got to show it, you can color it in d plus 1 colors. And let's let d be the max degree, the largest degree in G. We've got to show we can color it in d plus 1 colors. Well, the basic algorithm, let's see. First thing we do is we order the nodes in an arbitrary order. And we're going to show whatever order you pick is OK. All right, so order the nodes. Any way at all. Now, how am I going to use the induction hypothesis? I know I can assume that for any n node graph, I can color it in the max degree plus 1 colors. How am I going to use that to help me color G here, the n plus 1 node graph? Any thoughts? Yeah? Yeah. Let's create an n node graph by looking at these nodes and taking this one out for the time being. Remove the last Vn plus 1 node in the order. That leaves an n node graph. All right, so let's write that down. We remove Vn plus 1 from G. And that creates a new graph. Call it G prime with vertices V prime and edges E prime. So we create a new graph by removing that node. And we remove all the edges tied to that node. So for example, over here, let's see, the last node was 6042, so we take out 6042 and all these edges. And this is the graph that we're left with. That graph has n nodes. What's the maximum degree in G prime? when I pull out a node, can the degree of any node go up? No, I'm just taking stuff out. So I know that G prime has maximum degree at most D. The degree didn't go up of any node. Might have gone down, but it didn't go up. So G prime has max degree at most D, and it has n nodes. So we can use the induction hypothesis, Pn. It says that the basic algorithm uses d plus 1 at most, d plus 1 colors for nodes v1 to vn. Any questions about that? So if this were the n plus first node, the last node in the ordering, take it out. The basic algorithm now would take the same order here, v1, v2, v3, v4. Basic will color that in d plus 1 colors. And all I have left is to give this guy a color. And I'll have color G. Question? No? All right. So by induction, I've colored these guys, v1 through vn, in d plus 1 colors. All that I have left to do is color vn plus 1. And hopefully, we're not going to use color d plus 2, because then it wouldn't work. We got to use one of the first d plus 1. All right, so let's look at vn plus 1. And let's call its neighbors in G u1, u2, ud. It has at most d neighbors because every node in G has at most degree d. A neighbor is a node you're adjacent to. All right, so vn plus 1 has at most d neighbors, is adjacent to at most d other nodes. Now, what does that mean about the color I can use on vn plus 1? What do I know about what color I can use for that?
D plus 1.
Yeah.
It can't be any of the colors of U1, U2, so on.
It can't be any one of these colors that were assigned here. That's true. So how many colors got ruled out? At most D. And how many am I working with? D plus 1. So I got one left that I can use safely. Okay? So this means there exists at least one color in my set of D plus 1 colors that's not used by any neighbor. And we're going to give vn plus 1 that color. All right, so now I've colored every node in G, the n plus 1 node graph, safely, using a total of d plus 1 colors. All right, so that means the basic algorithm uses at most d plus 1 colors on G. That means Pn plus 1 is true. Whoops. And the induction is complete. Any questions? Yeah?
Could you also say start from the other way and start with like 1, go to 2 nodes, 3 nodes, at each step keeping all nodes connected to all other nodes, and then you could also see the same thing that your nodes are using more than equals 1 colors.
What do you mean by keeping all nodes connected?
All incident to each other. Doesn't like be a 4 node has an edge connecting to each other one.
Okay, so then I get a specific graph. I start with this. I add a node and make it adjacent. I add a node and make it adjacent. Yep. So you've constructed a particular graph. This is actually called, for the n nodes, it's called Kn, is the n node complete graph. Also called a clique, like a clique of friends, where everybody likes everybody in a clique. And in fact, for n here, if there's n nodes, what's the max degree? Max degree is n minus 1. What's the chromatic number of this graph? What's the minimum number of colors? N. They all have to be different, which is d plus 1. So you have built a special graph for which the optimal number of colors is d plus 1. But that is not a proof that this is true for all graphs. Because you've looked at a particular graph here. What's that?
You add it means that you can still use your less than or equal to sign.
I see. So you'd add a node and it's only connected to a few of them.
No, it's connected to all of them, but it still implies that you need less than or equal to the colors. It turns out it happens to be equal to.
Yes, in this case, that's right. So you've made an argument for this case where it actually is equal, but that only worked for this graph. It is the worst case. So it meets the bound. It shows you cannot improve this bound. Yeah, is there a question up there?
That's all I was going to say, is that you could prove that it was the worst case.
Right, so what you've done here is you've shown that I could not make that theorem any stronger. I could not replace it with D here, all right? Because you give an example where I can't get D colors, where the maximum degree is D. But that doesn't, to get a proof of the theorem, I got to go through all this. That wouldn't give me a proof of the theorem. They're not equivalent. One's an upper bound, one's an existence of a lower bound. This shows that for any graph, you need at most d plus 1. So any graph at most. That shows there is a graph that you need at least. And they are not equivalent. All right, one is for all an upper bound. The other is there exists a lower bound. So different in two ways that are important. All right, this kind of proof is very typical for what you'll see with induction and graphs. And you'll get a lot of practice with it. Are there any other questions on this proof? Okay. All right, so we've seen now by that example that we can't improve the theorem. In some cases, though, the theorem is way off for some graphs. Can anybody think of a graph where the bound we get from the theorem of d plus 1 colors is way off from the actual chromatic number you need, the number of colors you need? Yeah? What is it?
A graph like the one we got, you have like all men and women, like two sets of vertices and all the edges going from the left to the right.
Good, okay. Yeah, so what if we did this graph? Let me draw that. So you've got a bunch of nodes here, a bunch of nodes here, and every node here is connected to every node over on the other side. And if this is an n-node graph and I've got n over 2 on each side, what's my degree here? What's my max degree of this graph? N over 2. So D is n over 2. What's the chromatic number? How many colors do I need for this? 2. All right, so D plus 1 is way off of 2. There's an even worse example. Yeah?
You have one node in the center that's connected to a bunch of nodes radially distributed about it.
Yeah, the star graph. All right, so I got 1 in the center. I got n minus 1 outside. So here the maximum degree is n minus 1, just like a complete graph. But how many colors do I need? 2. So it's even worse here. All right, now what about the basic algorithm? How well does the basic algorithm do on this graph? Order the vertices some way. Color them one at a time, the lowest color. How many colors is it going to use? 2. In fact, it doesn't matter how you order the vertices. V1, V2, V3, V4. Because I'll color this one 1. What am I going to color that one? 1. Then I get to the center. What am I going to color it? 2. And now all the arms, what do they get colored? They all get 1. Whatever order you pick, you get 2 colors. All right, so now there's a difference between the theorem just gives you an upper bound. It says at most d plus 1 colors. But in fact, the algorithm can do a lot better than that, as on this example. So the algorithm might be a lot better. Everybody see that, what we're doing here? How the algorithm is better than the bound we proved by the theorem, even though the bound was pretty good for some graphs. Now, it turns out, I mean, we're not going to win $1 million for this algorithm. And in fact, this algorithm is sometimes very bad. And a really bad example is very close to this. In fact, actually, this one, let's look at how well does BASIC do on this one? Here. Make some ordering. V1, V2, V3. What's the BASIC algorithm going to do on this complete, we call it a complete bipartite graph. That's what this is called. I'll define bipartite in a minute. But what's the BASIC algorithm do here? Any idea of how, does it take n over 2 colors or does it take 2? Any ideas? 2. So take a vertex in the first one, say V1's here. It got C1. As long as I keep picking vertices over on this side, they're going to get C1. As soon as I get to a vertex over here, what color does it have to get? C2, because it's touching the very first one we had here. So when I get vertices over here, they're all going to be C2. When I go back over here, they're going to be back to C1. So actually, BASIC does good here too. Gives you 2 colors. Yeah? Those 2 aren't connected. But in this case, if I've got a vertex over here, it is by definition connected to the vertex over here. Because every possible edge is here. But that's a great idea. What if they weren't all connected? That's actually a great idea. Let's, in fact, the nasty example for the BASIC algorithm is very much like that. Let's draw it. Because so far, the BASIC algorithm is pretty much done perfectly on all the graphs we looked at, even when the theorem wasn't tight. So here is a nasty graph. And it is very close to the graph we just looked like, where all the edges are there. In this case, all the edges are there except for the one straight across. So if this is, the edge denotes likes, this is a world where you like everybody but your spouse. All right, so you have an edge to everyone except the one directly across from you. No edge there, and so forth. So it has almost every edge, but it's missing these edges. Now, the BASIC algorithm might do well here. What would be a good ordering for this graph? To label these V1 through Vn. Yeah?
Go through everything on the left side. Everything on the right side.
Yep, that's right. Because then, color 1, color 1, color 1, all the way down. One color for the left, What does this one get? Color 2, because it's hooked up against. And these all get color 2. So I've used 2 colors. Really good. Basic algorithm's looking great. Now here's a harder question. Can you figure out a bad ordering for this graph, where I use a lot more than 2 colors? What is it?
Starts at the top, goes across, then to the next level, and goes across.
Very good. V1, V2. Just as natural, really, if you think about it, to order it this way. All right. What color does V1 get? C1. What color does V2 get? C1, because it's not hooked up here. What color does V3 get? C2. What about V4? C2. It's not hooked up. It can't get 1, because that's up here, and it's not the 2, so it gets 2. What color does V5 get? C3, because it's hooked up to 1 and 2. V6? C3. It's hooked up to 1 and 2, but not 3. And you can see what's happening here. All the way down here, he's hooked up to all the n over 2 minus 1 colors. So he has to take C n over 2. So if you picked that ordering, not so good. You use n over 2 colors. So it really matters the ordering. Now I should say graphs like, actually any questions about what we did here? About this? All right, now I should say that graphs like this have a special name. They're called bipartite graphs. And that's important to remember. All right, so a graph is a graph G is said to be bipartite if the vertices can be split into 2 sets or partitioned. And we'll call them a left set and a right set, so that all the edges connect a node in the left set to a node in the right set. So in fact, a lot of today we've been looking at bipartite graphs because the nodes are here, like the men and the women, and the edges only go from the left to the right. And then it's called bipartite. And it's called bipartite because you can do it with 2 colors. They're in 2 pieces. So you don't win $1 million for deciding whether or not a graph can be colored in 2 colors. That's easy. You'll even do it for homework one of these times. You do win the $1 million for deciding if a graph can be colored in 3 colors. That's really hard to do. Now, coloring problems come up in all sorts of applications. You know, this company Akamai that came out of MIT we've talked about, we run a network of 75,000 servers. And they're used to distribute content on the internet and so forth. And we have to deploy a new version of our software on those servers pretty much every week. We're pushing new software out. And you can't deploy on every server at the same time because you got to take down a server to deploy new software on it. You've got to take it out of commission. And so we can't just take down all 75,000 servers because then all the Facebook and Netflix and all those sites would stop. That would be bad. And we can't do them one at a time because there's 75,000 and it takes a few hours for each one to go get the traffic off, stop it, load new software, and turn it back on. And it would take us years to do one software install, which we got to do every week. So we got to figure out a schedule for how many servers you take down at a given time and which ones. And it turns out pairs of servers have certain critical functions. So there's certain pairs of servers you can't take down at the same time. So we have a gigantic 75,000 node coloring problem, where there's edges between servers, nodes are servers, and there's an edge between them if you can't install new software at the same time. And so when it turns out, when you run one of these graph coloring algorithms on it, you could do it with 8 colors. It just turns out that way. So that means there's 8 waves of install that go on to the network. And now 8 times a few hours each means that we can do it in a day, and you can manage it. You know, on a much smaller scale, the same problem exists for register allocation, for variables. Here you've got to assign every variable to a register, but you can't have variables that are active at the same time associated with the same register. And you want to minimize the number of registers you need. So again, you have the graph coloring problem. The number of colors is the number of registers you need. And 2 variables can't get the same color if they're active at the same time, so you put an edge between them. The most famous example of graph coloring is the map coloring problem, or the 4-coloring theorem. And so here, every country is a node. Adjacent countries have an edge between them, because you don't want to color adjacent countries the same color, or you can't tell they're different countries. Now, the last example we'll talk about is an important problem in communication theory, communication networks, where again coloring comes up. Now here, you need to assign frequencies to radio stations or to cell towers. Comes up in mobile networks or just with radio stations. And if 2 towers have an overlapping area, they can't be given the same frequencies, or you get collisions between the towers. So suppose, and frequencies are very expensive. Companies pay the government a lot of money to get certain spectrum. So suppose you had this problem. Here's tower A, and this is A's range, where it reaches. Here's tower B, so it overlaps some with A. Here's tower C. Here's tower E. And here's tower D. All right, now the question would be, how many radio frequencies do you need? What's the minimum number of frequencies you need to enable all the towers here? Well, we can make that be a graph. There's a node for each tower, and an edge between towers if they overlap. C doesn't overlap with B. E does. E overlaps here, and then D overlaps here. So how many frequencies do you need for this graph? 4 would work. 3 is better. Can you do 2? No, you can't do 2 because you got here. But you could do 3. You could do 1, 2, 3, 2, 1. All right, this problem comes up. Did I screw up? Ooh, no, I can't do that. 1, 2. Yeah, much better. All right, this problem comes up all over the place. You will certainly see it sometime in your career. You'll have some problem where you're scheduling something, and it's really a graph problem in disguise. OK, that's it for today.